you. First of all, I would like to thank both of my audience for very kind introduction. And also, Professor Sandeep Juneja for inviting me to show time. Also, nice to see my former friend and colleague, Rajiv. Nice to see all of you. So today's slideshow, I thought I will talk about. I'm not going to really talk about AI because I'm not expert in that. I thought something about weather and climate models. I will talk because the climate change is happening. We are seeing all the extreme events. It's right? It's becoming one of the big problems. And I just want to tell that what are the lessons we have learned so far, and what is the way forward. This is a talk I gave in UX. Some of these slides are from UX open science. So just to give a brief, I'm sure many of you may be aware, but just as a repetition. So weather prediction, it has a big history, and numerical weather prediction. Weather and climate model idea, almost the basic ideas more than a century ago. And so as Professor Wilhelm Bjørknes from Norway, he actually said that weather prediction should be based on well-established laws of physics regarded as a deterministic problem. And so he conjectured that if you have sufficiently accurate knowledge of the atmospheric initial state, and this should be possible to predict. This was in 1904. It's basically weather prediction is the initial value. Okay, initial value. Yeah, atmosphere. And actually, there was attempts during the First World War by L.F. Richardson to solve these equations numerically, because computer was not there. By hand, he tried to use surface. And he also made important contributions to understanding to calculate these. And actually, his solution was actually a failure. Development for a small region. But later on, the way the solution failed, it was recognized later. And over a period of time, people started understanding this, making measurements of the atmosphere using radio sondes. They could get the vertical structure, temperature, and winds, and so on. And also, satellites came in the 70s, and they were all used to produce the initial conditions. And also, people began to understand the atmospheric dynamics, better understanding. And to solve these equations, numerical equations of the laws of physics, you cannot solve it by hand. I will show that. So you will have to use numerical approximations. So various stable schemes were developed. I think the big important one of the steps was the ENIAC computer, the first computer that came into University of Precipitation. And so these were big giants, Jules Charney, von Neumann. The main eye is a great mathematician, pioneer of computer. He used a polymath and Fjordhoff. They actually produced the first numerical integration of the barotropic water equation. This is a one-layer model of the atmospheric circulation. You can use it to, they made a numerical simulation for 2 days. This is known as a quasi-geotropic approximation. I'll not go into those details. They said that if you can eliminate in your initial condition sound waves and the gravity waves, these are very fast growing waves. So if there are some errors in the initial state, the errors will grow amplified very fast. And so you may not be able to predict accurately the large scale waves or the planetary waves because they are going to corrupt them. So this is the problem that L.F. Richardson actually faced, because he did not eliminate the gravity waves. So which later on they developed techniques how to filter out these sound waves and gravity waves. And so we had the first numerical model of the atmosphere at computer, which is 1950, and the first successful real-time weather forecast was by Rossby and team. Actually, but this was just a area just for the beta model, beta plane model, not a global model. And then another big giant was Norman Phillips. He generated the first general circulation of the atmosphere in numerical experiment. He could predict the monthly and seasonal pattern of the tropospheric circulation. And this was the beginning of the general circulation models. And later on, this was taken over by geophysical fluid dynamics system. And they went on to do climate model. That was the beginning. And over a period of time, I'll come to that about the climate model itself. Now we are talking about the weather models. Powerful electronic computers came and they could do all the massive calculations, computing power increased. And so when I say basically the principal laws of physical principles, we go back to Newton's law, right? So these are all the what is known as the Navier-Stokes equation. We have the momentum equation, which is basically the second law. And so you will see that this term is the Coriolis-Force term. You have the acceleration term, the total derivative, and it is, of course, when we talk in space and time, you have partial derivatives. And this is the Coriolis-Force term because we have a rotating time. And these are related to the pressure gradients. And these terms here, these are the frictional terms. This is basically indicating the transfer of momentum by the eddies and how to represent that. So that's a compound that. Yeah. And we have the thermodynamic energy equation, basically, which is the first law of thermodynamics is the energy conservation. And this term here that you see on the right hand side, these are the where all the processes that can lead to temperature due to diabatic, we call it as diabatic heating in the form of heat from the surface. It could be in the form of latent heat due to the condensation of water vapor to form clouds, which is very important in the tropics. And also many atmospheric constituents, they can track the long wave radiation like water vapor, the atmosphere. So all these terms, they can contribute to this this heating term, which is a very important component of the thermodynamic. And you have a mass conservation equation, what we call mass equation. And generally in the large scale, we are student that. Which is also a part of the momentum equation, but we drop the vertical acceleration. This is very important, having the hydrostatic balance, the large scale structure. And lastly, the water vapor equation, changes in the atmospheric water. This is a very complex part, especially for tropics. It becomes very important because we have the sources and sinks of moisture. There could be a source of evaporation, surface, and also precipitation is also part of it. So, yes. So, and water vapor is highly variable in space and time. So, these are the basic equations. This is basically we call it the. But then along with that, we add the water vapor equation.
But this mass density hydrostatic as part of the.
Yeah, that's also. Yeah. We have to have mass conservation. That's also part. And then we have to assume hydrostatic balance. So the question is now when you, because you cannot, these are all partial differential equations and they are coupled to each other. And so there's no way you are going to solve them analytically. And so basically what you do is when you try to solve these equations, equations of the motion of thermodynamics, you are trying to predict the rate of change of temperature with time. And then you want to discretize them on the grid, and you have different layers in the atmosphere. So if you make the grid smaller and smaller, you're going to increase the resolution. Your time step is also going to get small. So typically, if you double the resolution, basically the computational cost is going to increase fourfold. So typically models use something like a 10-minute time step starting from initial condition. And you have basically millions of equations. And now this resolution is even getting even finer and finer. And in the 90s, the resolution in the atmosphere was about 70 by 270. Present day it has reduced. Even now we are able to run our AMD forecast model, 12 kilometers global model. And so that's because of the thanks to computing. And we have about 64 vertical levels. And this is just the atmosphere. Now, if you want to include, we couple it with the ocean, because when you want to put longer time scale for a seasonal, you want to do climate change, you have to couple the ocean model as well as a cryosphere. So your computational complexity is going to really increase. And as I said, some of the physical processes that are happening within the grid, what is called a subgrid scale process, that you cannot resolve because the variables that I showed, they're all on grid points. But there are processes like very convection, deep convection, which may be within the grid itself. And there could be how the turbulent process, turbulent diffusion of how these eddies are going to transport heat and moisture and momentum from the surface above. So these are subgrid scale processes, and these eddies are very efficient way of transporting heat. So they can be from the scale of a millimeter to about a kilometer, but they are very efficient way of transporting heat. The fluxes from the surface, the atmosphere, and you have also the radiation, the solar radiation, which comes, much of it, about 30% is reflected, 70% passes through the atmosphere. It heats the land ocean system, then it is radiated back long wave. And this long wave can be trapped by water vapor clouds. And so these processes, physical processes, they cannot be resolved, and so they have to be parameterized in terms of the large scale variables. So various physical parameterizations are used. So now this famous work by Lawrence, this was he had a simple model of the convection, the atmosphere. He had three equations with three variables. And what he found, these are nonlinear coupled equations. And there are some parameters R and P and so on, sigma. And what he found out was, because it's an initial value problem, if I make slight changes in the initial condition, what will happen to the state of the system? So, so he discovered that even if you can see that these are two different, the forecast based on two slightly different initial conditions. Sometimes they start diverging, although in the beginning they are together. And he told me this is a plot showing it's an indication of temperature field. It can go from one, you start from one initial condition, it keeps going this kind of trajectory. This is the phase space system. You change the slightly initial condition, it will go to a different state. So this type of regime changes can happen. And so these are it's a deterministic equation. So almost perfect initial condition also, if you are having told after certain period, finite amount of time, you lose this skill. This is big discovery, and he called it as, so there is a limit of predictability. And the skill of prediction was only 2 days. People thought that. Why do you keep taking? Yeah, but because when we go to climate and we want to look at processes that are beyond, let us say, a month or a season, the ocean becomes a big part. You cannot restrict it to the and many of the things are, there's a phenomenon like called El Nino, changes in the ocean temperature that can affect the circulation patterns, precipitation, or the Indian sense. Yeah, ocean layer, top layer may be about, usually the top layer is well mixed. We call it as a mixed layer that can vary from 50 meters to 100 meters. So the top layers are very, very small. It could be 5 meters, 10 meters and so on. And you go to the entire vessel, it could be as deep as 3,000 meters, 4,500 meters. So when you go to the deeper layers, but not much happens. So those are on very long times, maybe thousands of years of deviation. So for the seasonal time scale, only the top layers.
So you mentioned the Indian body that you have.
Yeah.
12.5 kilometers, 12.5 kilometers. So the whole world,
Yes.
including the ocean?
Including the ocean. Yeah, but that model is just an atmospheric model. The sea surface temperature is because we are typically looking at 2 days. We are not about 10 days forecast. We don't go into the season. So the moment you go to the season and beyond, then you have to. Right.
You're doing 10 days. I don't really take to get to.
Yeah, they are doing it day in, day out. It takes 2 hours to run. 2 hours, 2.5 hours. Yeah. And yeah, very powerful computer. Yeah. So basically, he set the limit of predictability, theoretical limit of predictability of 2 weeks, and this is mostly for the extratropical systems. So this I'm showing what is the current state. This was in the 1960 and by Lawrence, 1963. And now this is one of the famous weather, the leading weather center. And we have one in India, the National Center. European Center started in they focused heavily on the data simulation because initial conditions. And this is a way of combining various observations, various platforms, from satellite, from ships, ground-based observations. And so the model keeps making there's a kind of forecast trajectory by the model. Then you have intermittent observations coming at different times. And there's a way of combining this data, the observations and the model, produce what is known as the analysis. Then you keep forecasting it. So this entire cycle keeps on going. And over a period of time, satellites have improved, more observations are coming. Earlier, the southern hemisphere was only sampled. Now, even the southern hemisphere, because of a lot of oceanic area in the southern hemisphere, now more observations are coming even in the southern hemisphere. So, what is shown here is the kind of a skill score, and how the skill score of this is a parameter known as the 500 millibar height. This is typically from the midlatitude circulation. How good we are in predicting the midlatitude circulation. And what is yellow line? So this blue lines, one is for the northern hemisphere, one is for the southern hemisphere. These are the speed of 3-day forecasts. The red is for the 5-day forecast for northern and southern hemisphere. Green is for 7-day forecast. Yellow is 10-day forecast. What it shows is now, if you look at this is 80% skill score. Suppose you extend this 80%. So in 2020, suppose we are getting 80% skill score. This in the 7-day forecast, this was there. Similar thing in 1990s, we were getting in the 5-day forecast. And when you go back to the 3-day forecast, this was there in the early 80s. So the skill of the forecasting, you are getting a longer lead time thanks to the data assimilation. So continuously, they are making improvement in the skill of the forecast. And it's not only extratropical circulation, many features of the tropics, because the tropics are dominated by the convection and the clouds. And we have these satellites like the Meteosat, our own INSAT. So they're giving this snapshot of the cloud movements, and models are also able to get these very large scale organization clouds. But within the inside, how the mesoscale convention develops, still there are issues with that. And which is becoming one of the challenges. So models have improved over a period of time. And this was a very nice paper that came out by Bauer et al. The NW numerical weather prediction is the story with started. They say this computational problem weather prediction is comparable to the simulation of a human brain or the evolution of early universe. And this is performed every day, day in, day out at all the major centers across the world. And this has become a big success. Actually, and it has been, although many other fields like they have the aura fundamental physics breakthrough, this is also a very great revolution that has happened. And so this, and it's a very, and now people are not just looking at just from one initial condition. There are ways to perturb the initial condition. You have an initial state, so you can generate an ensemble of initial conditions, an ensemble of forecasts. Then you can use probability method, say what is the probability of precipitation. So this is becoming very popular even for the tropical cyclones and so on. And so this is just, I thought I'll show something from our own NCMR that we have recently. So tropical cyclones we have done very well. So the problems in the Orissa super cyclone in 1999, then more than 10,000 people died. But now our skill of tropical cyclone prediction is improved, and it's in single digit or maximum double digit, less than 20 deaths you see. And this was a typical example of a system in Gujarat that produced heavy rainfall during 26 to 28. And there was a low pressure system that went from, I show in my next slide, and that was producing this heavy rainfall. The model forecasts were able to get that. And simultaneously, a little later, another system was forming. And this actually went on to become a tropical cyclone later on, which will weaken. So weather prediction is a success story. Now, what about it doesn't now stop there? Other problem that is what we are seeing is the climate has been warming. This is the 2023, the global mean temperature crossed 1.5 degrees. It's all mainly because of human activities, only because of the greenhouse gases like carbon dioxide, methane, which are absorbing the long wave. And so with climate change, and of course, when you go to the climate change, science of climate change itself, it started with Joseph Fourier in 1824. 1824, he was talking about the glass bowl effect, how these greenhouse gases can trap the long wave radiation. And it can warm the planet. Then John Tyndall. I think one important contribution came from Svante Arrhenius, a Swedish scientist. In 1896, he quantified the change in surface temperature to be expected from doubling of carbon dioxide. He predicted it about 5 degrees. He did not have moisture. He did not have convection, vertical transport of heat in this one. And subsequently, and also observations began by Charles Keeling from Mauna Loa from the 50s. They were able to make very precise measurement of the atmospheric concentration of carbon dioxide, greenhouse gases. It's still going on. This is known as the Keeling curve. I think a fundamental breakthrough happened by Manabe and Strickler in 1964. They said that vertical convection is very important. It's not just the radiation. So the moisture, how the moisture feedback happens. So they developed a radiative convective model to compute the thermal equilibrium. And 1967, they went on to, this was the paper that won the Nobel Prize, and in physics 2021. And they also had an experiment where they doubled the carbon dioxide, and they showed that could amplify the warming, just not just the carbon and water vapor feedback as well. And so this was a cutting edge. This was 1967, and I had the good fortune of working with Manabe, Japan. He was my boss. And so this is the 2021 Nobel Prize, Manabe and Klaus Hasselmann, they shared it. And also the Giorgio Parisi for the disorder and fluctuation of physical systems. So the important contribution is the radiating convective model he introduced. How the radiation, convection, and water cycle can influence the climate and it was and one more important contribution. This is the Manabe in his Princeton and his boss, Podgorensky, who started with PFD, the first founding director. And so this is a paper from the Nobel Prize committee. So at the surface, you see the troposphere as you go up, the temperature decreases height, and in the stratosphere it increases height generally, the normal. So with global warming, the troposphere gets warmed up. Also, the surface temperature increases. But in the stratosphere, it actually cools. That's the important thing. Now, discovery that he pointed out, and now people are able to see this in the satellite data. Yeah, now, of course, then periodically you have assessment of climate change assessments. So the 6th IPCC assessment report has clearly told that the warming that we are seeing since the 19th century, it cannot be explained just by natural variables. So the human has really increased, human influences really contributed to this warming. I will not go into the details. Yeah. So if you want to study climate change in its full complexity, you cannot just talk with the atmospheric product. You need the ocean, and because we are still talking about longer time scales, you also have to have the carbon cycle if you want to see all the biogeochemical processes, both in the land and the atmosphere. And there are also changes in the atmospheric composition due to aerosols and chemistry. And also there are changes in the glacier melt, and they can in fact affect the sea level rise and so on. And so if you want to really look at all these different components of the Earth system, you really need to go to the Earth system models, which is fundamental for studying climate change and also their impacts. And so basically they provide information about the physical, chemical, biological mechanisms governing the rates of elements of the Earth system. And we know that this is again from the IPCC assessment that these are different future projections of the global surface temperatures. Right now in 2023, we are 1.45 degree compared to the pre-industrial. And in the future, the warming is projected to increase. These are different scenarios. This is a kind of very high emission scenario. These are what are known as shared socio-economic pathways. They're not going into details. These are very high emission scenarios where you can cross the global mean temperature to be 4 degrees. And this is a very sustainable path. So right now we are somewhere in the middle of the road. 245. This itself we will cross the 2-degree mark by end of 21st century. And one of the consequences of this increasing temperatures is that the patterns of this warming pattern is not uniform because most of the warming is concentrated in the polar region, in the high latitudes. The tropics are also warming, and these are from the model projections, and this is the observed warming present day. And associated with warming, the precipitation is also going to increase in many of these areas. But also the areas in the subtropics, the deserts, where the air actually sinks, they are going to get drier. So the variability of the precipitation is going to increase. So the wet regions are going to get wetter, and the dry regions are going to get drier. So the variability is going to increase. So that means some of the areas which are drought-prone areas, the drought could become severity of the drought. And one of the consequences, why I'm going to this thing is the water vapor feedback is a very important mechanism because the temperature increases, the water holding capacity increases. And with every 1 degree warming, it could be anywhere between 6 to 10% of water vapor. So the direct consequence of that is the heavy precipitation events will increase. And typically so the heavy, extreme temperatures are going to increase both in frequency and also intensity, and also heavy precipitation over that. And with the 2-degree warming, we can have a 14% increase in the heavy precipitation. This is just by thermodynamic argument. But now, what does it mean for the monsoon region? So it's a much more complex issue now. It may not be simple Gaussian-Clapeyron equation. Because when you look at the monsoon precipitation itself, this picture, it shows the regions of rainfall, seasonal rainfall more than 100 millimeters, 100 centimeters per season. You can see along the Western Ghats, Central India, and also hills. And these are produced by various systems like monsoon low pressure systems, depression platform in the Bay of Bengal. And there are also some systems known as MTC mode, Gujarat they get used. And there are these cloud bands moving from the ocean to the towards Indian subcontinent. So there are different time scales, different time and space scales. So it's a multi-scale interaction. That is what gives rain to the monsoon. Now I'll give some examples. That's what I want to quickly go through some of the events that we have seen. The June 2013 Uttarakhand event, which led to heavy rainfall and floods of the Himalayas. And this was a kind of interaction between the monsoon and extratropical circulation. Then also about the late 2010 flash floods. These were mesoscale convective systems over the high terrain of Leh Ladakh. And heavy rainfall over Gujarat and Western India. These are the monsoon rainstorms. We did some work. And I will also talk about the July-August 2022 floods in devastating floods in Pakistan, but in the basin. Just these examples, and this famous, this was a huge disaster that happened in June 16th of 2013. And we looked at this paper by Vellore et al. And the Shiva statue was badly damaged. Kind of improved, they made it all right, they repaired it. So we looked at 34 such cases of events in that region. And it turns out that during this phase, there was kind of early monsoon onset, and the low pressure system went through the Bay of Bengal very quickly. And at the same time, there was also a very deep trough almost coming from the polar regions. This was moving very slowly. So in the this low pressure system was taking the moisture. Mid-tropospheric, there's a convergence between these two systems. And that kind of flared up this heavy rainfall in that region. Not going into those details. So you can see this is the 13th June, 15th June, 17th June, a low pressure system going from Bay region, and it was taking a lot of moisture. These are the precipitable water anomalies. And this is the extratropical trough, which is slowly moving. And this interaction was led to that heavy rainfall event. And the problem is the rainfall amounts can be in a day, 24-hour accumulated precipitations, again from the IMD, could be something like 400 millimeters, more than 40 centimeters rainfall. And several cases close to 400, 300 millimeters of rainfall in 24 hours. It's a very steep terrain. So it can lead to runoff and major flooding.
So that this trend coming up few days in advance.
Yeah.
You can predict the rainfall.
Yes, yes. There is a, don't think there is IITM model also they predicted, but they could not get that kind of intensity. This kind of heavy rainfall, if you are getting in 1 hour, 1 day, if you want to get 40 centimeters or 10, 50 centimeters, I think models, probably that's where if you have a lot of data, maybe the AML, getting the intensity of rainfall.
These models also include topography.
Yes, yes, they will. So there are problems with the parameters. It's heavy rainfall. Models have some questions because we have to solve, we have to take care of the numerical stability. Model is not wrong. Sometimes we make it too stable. So we are not really getting those big effects. So the precipitation process, I'll come to that. And this was another case by Bob House and the Leh flash floods. Leh is a very, or you all know, it's a very dry place. And it's located at a high altitude of 4,000 meters. So immediately after Pakistan 2010 was a big flooding, late July. A week later, this Leh also experienced some flash flood. And now what they are telling is when you look at the satellite data, this is again from the Meteosat, because the land gets heated up in the daytime. And so the convection develops. These convection, diurnally generated convection develops. And by evening, they start moving westward. And at the same time, if you also have some kind of a low pressure system in the Bay of Bengal moving, these two can really interact and produce very heavy rainfall. And so this is a kind of schematic by Rasmussen House. So you have this Tibetan plateau. So these are diurnally generated convection systems. They are moved by afternoon, they develop and move westward, and then you have this moist air coming from the bay. So the moist air can quickly rise up, and the dry air will sink, and this will give rise to the deep convection in the sloping terrains.
So are these variants which are happening? Still meeting of different
different types of air masses.
the rare events, they don't happen at different sure.
They are not, but they can happen. Yeah, they are not that 2010 it happened. Lately, quite a few we have seen. Not every year perhaps, but they are happening.
So do they always lead to massive rainfall or is that just the most?
Yeah. At least this particular event we have seen. But so we have to watch out. These are the things that we are beginning to understand. And I will come to some of these issues there. And the other one is this Gujarat. This was the recently 26 to 28. There was a big deep depression of this place, and the IMD had also forecasted heavy rainfall over Gujarat and Western India, and this was also warned by IMD, even the red alert. And these are known as the rainstorms. Rajivan has done a lot of work on this. And these are the forecasts by the NCMR model. They were able to get it in the 24-hour, 36-hour forecast. And also this later on went on to become a kind of a tropical cyclone known as Asna weekend. So why I'm showing this is people have known these kind of things. In fact, this was a paper by Auroop. They have looked at the severe rainstorm, most severe rainstorm of India. This was in 1941, 1 to 5 July 1941. And one station here, Dharampur, recorded almost 947 millimeters of rainfall in 1 day. And that's a kind of record. It's in Surat district. And then everything was disturbed. And it was a low pressure region. It's a very nice work by Surat, Bombay, and so these monsoon rainstorms are, And you also have my own guide, Professor Keshavamurthy. He discovered what are known as these tropospheric cyclones. The cyclonic systems, they are pretty much, they don't move much, they are stationary. and you don't see at the lower level, but they can need a lot of rainfall. So these are some of the 3-day accumulations: 700 millimeters, 650 amount of rain, and you see when this happens, the cloud band is a very large cloud band extending. It's not just good. And within this very large cloud band, we have this mesoscale getting organized. How to get there? So see the movement, whether this is going to be the catch. Although you see this very large scale structure, these embedded cloud systems, convective systems, they can produce a lot of rainfall. And we also understand because how the heating patterns we have and what drives these tropospheric cycles. So we'll not go into those details. And yeah, this was we looked at some of the monsoon rainstorms. Dr. Rajivan here written a paper with Sagar, and we looked at the Western India. The recent article will be appearing. We are finding that these rainstorm events over Western India, both their intensity and their duration has slightly increased. And it turns out that many of these rainstorms over the Western India, they are seen during this IOD years. There's something called the Indian, it's like the El Nino Southern Australia. It's a kind of mode of variability here, which leads to patterns of seasonal temperature changes. And so this during this positive IOD years, there is very strong winds off the Sumatra coast. There's more upwelling, cold water comes up. There's a lot of evaporation, and this water vapor is transported into the Indian region. It seems to trigger this heavy rain associated events and heavy rainfall over Western India. So what I'm doing, there's a lot of nuance to this. Just going beyond. So the question is, what will happen to the warming climate? Because that is going to influence some of the precipitation patterns. And quickly about the 2022 Pakistan, it was very, very extreme, and it was one of the massive devastations that happened. And before that, before the monsoon season itself, there was an intense heat wave. And so pre-monsoon heat wave, many places, temperature in April, May past 40 degrees. There was one place that also reported 51 degrees. And also some of the glaciers in northern mountains, they had melted during time. And they also added to the runoff. And as I said, due to human-induced global warming, the downpours are also going to increase. And more importantly, there was other factors like there was a very strong La Nina. La Nina is the opposite of El Nino. They have a kind of a cold sea surface temperature in the eastern Pacific. Western Pacific is anomalously warm. And generally, when this was the 2022, you can see there is a lot of moisture getting transported into this region. And with this strong La Nina, it tries to push all the circulation patterns more westward, which we have seen. And the rainfall in this region has happened in certain spells. Now the question is, and several studies have come out of this, and actually there is a 3-year La Nina, so continuously 2020, 21, 22, not as a triple dip La Nina, very long La Nina. The 22 was pretty intense in this region, and apparently the moisture transport into that region was very important for triggering the event. And this has been shown, and also the monsoon, several studies are showing that the heavy rainfall was triggered by, that was the trigger for the flood in the 2022. And they are arguing that in future, this region is warm, and the monsoon precipitation is going to intensify. Heavy rainfall and flooding is quite a few papers have come out, and this was another paper. They're able to attribute the heavy rainfall and flooding to climate change. So this was, as I told, May 2012 also there was warming. By 2022, the warming was here. So event attribution studies have been done. And also one thing is, as I said, this very strong La Nina was there, warming in the West Pacific, cooling in the sea surface temperature, cooling in the Central and East Pacific. And this was very instrumental in driving the circulation changes in the atmosphere. And so while Pakistan region was experiencing floods, China was having very severe drought, the Yangtze River Valley of China. And the rainfall was deficit, heat waves were very strong. So people are talking about the recent paper that talks about the La Nina gradient and extratropical thermal patterns. They have driven the 2022 East and South Asia seas of extremes. So climate change impacts the way it is had, and several papers. This was another paper by Hong et al. So you had heat waves over China, Europe, heat waves, Pakistan floods. So La Nina seems to be an important driver. Same thing happened in 2010. So it's not just we are looking at Pakistan or any particular region. These are changes in the entire climate system, and that's what we have to keep in mind. So one of the other questions: what will happen to sea surface temperature gradient, the warming climate, global warming, whether you will have more El Nino or whether you will have La Nina? This has been a very important discussion. Now it looks like people are saying that the warming, the global warming, we are going to get marking rule. And so earlier the local people thought El Nino's problem looks like the La Nina type of pattern between the circulation atmosphere and the shift westward, and it has a profound influence on this monsoons and so on. And so when we look at the projections from the model, from the CMIP6 models, we find that these are for the historical period. Models are able to by and large say that if you are having greenhouse gas, you are going to increase more precipitation. Whereas the aerosols, they try to decrease. Cooling or to reduce. But in the future, as the global warming continues, monsoon is projected to increase. But there is a lot of spread across the models. There's a lot of uncertainties which we have to reduce. So how do we improve the uncertainties? Quickly. So one is this, the key processes. One is the organized monsoon convection cloud system, mesoscale system, which I showed. And they are very, very important. Also, we have to know the coupling between the atmosphere and the ocean convection. And also the ITCs and the intertropical convection. These are the rain beds. I will show quickly. That is one area where you can process. We have to improve aerosol and cloud interactions. And what are the approaches? Some people are thinking that we should go for a kilometer scale model. It's going to be complex, very, very expensive. Other things now people are telling that new developments like AIML methods, you can extract patterns using the geospatial data. And some people are, there's another approach called model hierarchies. You cannot go with one model. You have a hierarchy of models, right? So on. And Kelly Emanuel has written a very nice article. He says, for future advancing the basic understanding, you have to combine theory, observation, model. You have to take a very balanced approach. And start moving. Start. Battery is yeah. I have a few more slides.
Let me do it. Yeah.
Yeah.
Does it change or?
Second weird.
Okay.
Not sure. Should I then, should I do? Let's take here. What this one? What is that?
This is the presentation. We have to go to the slide.
Yeah. So we have to definitely improve. So this is our own IIT Earth system model. We developed at institute. We also participated in 6 experiment, and now we are planning to improve the go for CMIP7. And many things are improving the CA is many improvements. It's a radiatively balanced system. And we have also used it for our own assessment report. Even for the Ministry of Earth Sciences. It's a reasonably good model, climate model, but still it has certain problems. We need to work on that. One of the things which I personally feel is these ITCs movements are going to be very important. And this is the region of where the maximum cloudiness happens and the convergence of air from different hemispheres, intertropical convergence. So this is the position of ITCs that during July and January it's south of the equator, and all the cloud systems are going to align across this ITCs there. And people have studied actually this very important. So this ITC basically is governed by the global energetics, but local physical process becomes important. And so one is it has a global structure. The energetics is basically going to depend on the hemispheric energy balance, but how the convection regionally or India or West Asia, West Africa, the local process becomes very important. And just to give you an idea, this is June, July, August, September. This is the observed position of the ITC set, and this is from the IIT and BSL from our model. There are some biases. We need to first improve the ITC set. Whether AI/ML can play an important point. And the problem is worse in summer generator. Especially you can see over the Pacific and the Atlantic Ocean. This is the observation. ITC set is actually to the north of the equator. But here the model is showing south.
We'll go back.
This is for June, July, August. So these are the how to improve. These are the questions that I've asked. Probably there's an opportunity. So in summary, I just want to say that so precipitation extreme, the changing climate has big severe impact. I think the water problem is going to become a big issue. Water scarcity is already affecting 40% of the global population, and water-related deaths account for 70% of deaths. This is from the World Bank. And monsoon precipitation extremes, major cause for droughts and floods over monsoon region. These are big impacts societally, infrastructure, economically. So I discussed various flooding events, examples that I covered. And so the drivers of extreme precipitation, of course, climate change, there is acidic gradients, Indo-Pacific acidic gradient, pre-monsoon heat waves, monsoon depressions, moisture transport, associated effective systems. A variety of processes, it's a multi-scale process. So how do we address them? So definitely we need improved understanding, scientific understanding we have to improve, and also we have to improve the ability to predict heavy precipitation in a challenge, changing climate. We have to take an up system approach. We cannot just look at the atmosphere because there are different scales involved. We have to look at the atmosphere, ocean, land, biosphere, human activities. And you need a lot of research and development to detect and attribute the prediction of the extreme. You need many ensembles of experiments. We call them as large experiments. Also field experiments for having the observations, strengthening international collaboration, education, training, and research. And more importantly, we have to have enhance our early warning systems, which means you need observations, satellites, radars, balloons. They are going to be good and very key. And satellite retrieval of the vertical profiles of water vapor and winds. This is a very important problem. Vertical variation of the wind is going to be important, and it's a key for predicting heavy precipitation. And we also need to improve high resolution. High model, we have to move to high resolution. But that alone cannot help. We need to improve the physical process to bring new techniques like AI or data. And we have to link the research, whatever research we are doing, to operation and application. And the basic research, operations, capacity building, they develop tailored applications specific to sectors and regions. And we need a coordinated strategy. We have to go with the water people, the agriculture people, transport, disaster management, health, and so on. So these are the points that I want to share. Yeah, thank you all. Sorry, I didn't have much AI. We start and keep it very general.
Sorry.
Yeah.
When you talk about Lawrence, you said that when you put out the initial conditions with the outcomes were very different. Then in ensemble forecasting, you also put out the initial conditions to get like a wide range of forecasts. So how does the like perturbation not lead to very different forecasts?
Yeah. So of course there is a, you also want to have the it all not become flows also, two flows. There should be a divergence. So the idea of perturbation is you get a probability. What is the probability of this being false? So that's why the examples are.
How accurate is that?
It's working very well.
Yeah, no probability is very realistic.
Very realistic, especially for tropical cyclones, we are giving the strike rate, strike probability in a particular area. So the location track is good. Tracks, they are doing a pretty good job. In terms of the intensity still is a problem. And we have to have many samples because probability is going to be, because we cannot tell exactly this place. We have to be around in the probability of 70%, 80% we get this area. So that's a way to go forward.
You talked about there was a data process where you the inferences of models and somehow there was a cycle that you also use real life like where the process uses real life observations as well. Then you get to the product cycle. But I got a bit confused there.
Oh, you mean the data simulation?
Yeah, data.
Yeah.
What I what an instrument is a lot of data. You keep an eye and your predictions become more precise. But then what you need is cycle.
Yeah. So when what I mean is like the forecast cycle forecast is being run. So I make suppose I want to do a 10-day forecast. So I run it for first 6 hours. By that time, observations come. There is something called global telecommunication GTS system. So observations all over the world, they will come to the NCMR. AMD will come to NCMR. So you have a forecast of the model in 6 hours. Then the observations are coming, they know to combine. So they will make a new analysis after 6 hours. Again, launch another 10 days, a 10-day prediction. Then after another 6 hours, again, they will have new observations come. So you have a forecast, your simulation cycle, you have a forecast cycle. This cycle will be continuously going. And they will be combining observations as and when they are coming. And so this process they have perfected for a period of time. It's an amazing thing that so observations all over the world, from India, US, to different platforms, they're coming to one place and they're all following the same procedure. Quality observe, you have to make quality checks, which observation is suitable. Then the model is giving, you have a way to improve that. And there are variations. There are different techniques. That itself is now a big ocean. And they do that for the ocean as well. Ocean assimilation. So it's a lot of engineering, mathematics, and
Mathematical fitting this.
absolutely. It's a mathematical.
I think people in India will also do
Yes, in NCMR, people are doing it. Of course, we collaborate with the people and so on. But that itself is a big ocean. To get into data assimilation, you can spend your whole day. And the thing is, the new satellites are coming. Now sea level altimeters are there. So they're blending that. And temperature. So as now when you go for now ocean color, chlorophyll is coming out. So you can want to study biological process. So people are now talking about Earth system assimilation, not just the atmosphere or ocean. The Earth system they want to have forecast. That's the way. What will happen to fisheries, all these nutrients, chlorophyll and those things. So this entire biological process. So this is good observation and model combined. And new satellite, I think satellite is going to be a big remote sensing, and that's how we are going to monitor. Without that, we cannot. So that's why Manabe is to always the two things: one, green model, green satellite. This always you remember. And of course, we need in situ observation. We cannot put everywhere, maintain that. So these two have to be.
You mentioned about getting data from multiple sources. We are looking. Either option which takes care of this. The data comes in a format which can easily be.
Yes, yes. So there are different codes, some buffer format, and so there are standard ways how to read the code, station as a code and what kind of, so all those flags, everything is there. So after that, people trained to handle that. Once you go there, you will also learn about it.
The centralization has been done.
Standardization, everybody follows the same.
Yeah, I had one in the problem. To what extent will improvements in mathematics like on better discretization or better architecture will help you make this consistency 100 kilometers to 10 kilometers?
Reading. Yeah. So my personal views, I think in terms of discretization. See, in fact, we had used a model regionally to do for India, so we can solve it. And then, but we cannot do it everywhere. So we make it force or outside. And that's it. And because it captures the way, because the monsoon needs to be interacted over. And so, how you develop your financial schemes? Very good. And I think some people have spent time on it. And because in the process of making things faster, we have developed schemes where we need a stable scheme so that the model doesn't go. We increase the time step very fast. I think we are making some compromise. This is what I get because in terms of model, it has a time step of the physical process is smaller. Time step of the dynamic, which means what I mean the public scale process. And the time step of the dynamic is very larger. And it has very small time step. So small, so you don't allow the errors to grow very fast. And that's probably one of the reasons why some of these, and also the second law is the rainfall second order of it. It's very extreme for it. And also it also depends on how the water is sufficient to work at moving forward. So generally earlier method, what the for example Manabe is a very good advocate of it. When something gets unstable, you will adjust the landscape. But it makes also your things very stable. So you will not get very heavy rainfall. And I used to discuss it. The people have made so many changes and they want my scheme is the best. The one convective adjustment, it makes the atmosphere stable. And but he says it's not good for the numerical weather condition. Just for climate model, it's important. And useful for the numerical weather prediction, bed still and scheme, which is again based on my scheme, is the one that works. But I think it goes beyond that because it's not only climate people, they want to make that scheme. So that the model keeps running. So they get all this tropical convection rainfall. The way the water vapor is converted out, it's precipitating out. Yeah, that's very important. We have to really focus on it. So,
Thank you so much. Thank you.
Thank you.
Yeah, I guess we have one more task for you.
Oh, okay.
So we'll go ahead now. We won't take a break, but we'll go ahead with tutorials by Mr. Rajivan. I request you to
Yeah. It's my great honor and pleasure to welcome Dr. Rajivan. Give his second talk and Rajivan is my boss at the Ministry of Earth Sciences, Secretary for Earth Sciences. Also my good friend and was also served as director of IIT this period. And He has more than 35 years of service in meteorology. And presently is the Vice Chancellor at AIA. He's done a lot of work on the monsoons, expert monsoon, and was involved in the seasonal forecasting and network. And he's very knowledgeable. Also, he worked at NAR. And we both share the common trait is the 8%. So I have known him for almost 40 years. So welcome, sir. Thank you so much. So, before you go,
who were coming up for. Can somebody help me to upload this presentation? Yes, sir. Maybe. Go to Ashoka. This one. Yeah, this is one. Huh? One by one. Fine, fine. So we can go to.
you're going in great condition. Thank you. Thank you, Dr. Krishnan, for visiting me and to thank good friend Sandeep for inviting me. Thank you, sorry, for hospitality. So I'll be giving you my presentation. So it's basically not a presentation, it's I have a tutorial. So I have to give 3 hour tutorial. Okay. Yeah, so I given it in free. Yeah, the first part, so what I will do is basically it's now control modeling. I will talk about what we mean by the way we should really model and important. The basics of some of the things we start not discussing now. So I will repeat it if you don't mind. And we just to have the completeness of the presentation. And it's looking well. This one is there. This one is there.
We have another. Okay.
Yes, yeah, good. So this is the way I will be taking the. So part 1, I will be talking about the basics of monsoon and in monsoon and its variability. Monsoon is has a dawn variability because there's no variability. There was no meaning of we have prediction. Predictions become important because monsoon varies. Part 2 will be on given the predictions. Most of in detail.
what are different techniques used for only. That part will be what's the percent skill of our IFTs, IFT forecast, we make it here. What is the prospect for AL and what we should do into this forecast? You can interrupt me and ask questions when you want. Okay, so the sun is our energy, source of energy. So sun, we will not have weather and climate. And we receive some X amount of energy from sun, and the same X amount of energy is given out to the space by air system. So there's a balance between energy received and going out. So temperature is same. Temperature is fixed at 20 degrees Celsius. If you take off temperature of the whole globe and average it, you get. And now climate change is happening because the energy which is going out is reduced because of the heat. And so that we get more energy and the system of more energy. So temperature goes up. That's the basic concept of climate change. So sun drives weather and climate. And so we have this so-called cycle, seasonal cycle, because of the movement of sun. Sorry, movement of earth around the sun, and sun to earth are oriented of the peak. And so we have 4 different seasons. If you take a place like in Dubai, this is Dubai's temperature. Yeah, this is Dubai's temperature for different months. You can see that red is maximum and blue is different temperature. You can see that this is a beautiful cycle. It simply goes with the sun. And so you have a maximum around July, August. Whereas if you take a station like in Nagpur, this line is the temperature. You can see that temperature is peaking around May. And suddenly it drops in July because we have much. Whereas Dubai don't have the influence of Dubai's annual cycle is different, and whereas India's annual cycle is different. These vertical bars are basically rainfall over. You can see that the rain, because of the monsoon we have, temperature goes down. So here the definition of season is winter, spring, summer, autumn, that kind of thing. Whereas we talk always of in terms of monsoon. Winter, pre-monsoon, monsoon, post-monsoon. So because we are more close to our monsoon, monsoon is our bread and butter. So we have to have seasonal also is classified. And we have 2 monsoons. Actually, we have 2 monsoons. One is southwest monsoon, that is the rainfall during monsoon season. Southwest monsoon season, this is the rainfall during northeast monsoon season. This basically occurs between October to December, but it is confined only over southern parts of the country and over northwest India country. So we are lucky we have 2 monsoons. Okay. We are fortunate to have 2 monsoons. And if assume that we did not have a monsoon, it would have been something like Somalia. It will be carrying AK-47 and roaming here and there. So we are fortunate, we have 2 monsoons, we have plenty of natural resources available with us. And so I will briefly talk why monsoon is, what is the basic area, basic dynamics. And as I said that seasonal cycle of temperature is controlled by the position of sun. So during winter, this is the temperature, you have cold temperatures here, warm temperatures in the ocean. The temperature gradient is from south to north. Whereas in May, June, July, the temperature gradient gets reversed. You get maximum more temperatures over land and low temperatures here. So you have temperature gradient from north to south. That reverses. Okay. And if you really want to see the vertical profile of temperatures, this is the vertical profile of temperature in the atmosphere, height of the atmosphere. So we have a lowest 10 kilometers for troposphere, and most of the weather occurs within the troposphere. So the troposphere is more important, and there is some influence of stratosphere on weather, not over the mesosphere. The atmosphere doesn't have any role on climate. Stratosphere plays a role. Okay, so when temperature is high, you get low pressure, because warm is low pressure. And so in December, January, February, the pressure is high here and low here. Because the temperature is low here, so pressure is. And here, when temperature is high, pressure is low. So the pressure gradient here is from north to south here, and whereas in the monsoon season, pressure gradient is from south to just reverse. And according to the wind direction also is changed. And during December, January, February, we saw northeast trailing winds, whereas in the monsoon season, the southwest monsoon season is all southwest. The pressure gradient wind flows from higher pressure to lower pressure. The water flows from higher pressure to lower pressure. Wind also flows. Only thing is, so here the pressure is high here and is low here. The wind should flow from southern hemisphere to northern hemisphere. But once it comes, and these winds are not oriented exactly south to north, mainly because it's a influence of transportation, I suppose. The southern hemisphere here it will deviate towards left. The northern hemisphere it will deviate to the right.
So why is there a pressure gradient?
The pressure gradient is different because of the temperature. Temperatures are different.
That's good.
It basically is driven by. Okay, so this is a beautiful flow of monsoon flow. So you get it's at about 1.5 kilometer before, and you can see that the flow, the monsoon flow comes from southern hemisphere, crosses the equator, and goes on, and then here it gets again towards here, and we call this as the monsoon trough, and most of the low pressure system form here and so the maximum flow, maximum wind speed is something here. We also have strong flow here, and we have this Somali jet we call here. And so what it does basically is a lot of moisture from the Great Ocean. So a lot of moisture breaks to it.
So it's a very important. You said we have two different modes. Now see how much is for.
Yeah, so about 70 to 90% of rainfall in the country is contributed by southwest. 70 to 9. And 70 is basically for Tamil Nadu. The Tamil Nadu gets maximum, sorry, the countries like from Andhra Pradesh. There, they get more rain in October. Tamil Nadu is almost 50. They get a lot of rain in October. But most of northern parts of Kerala, like UP, Bihar, and maximum rainfall comes from Maharashtra. So that's the bread and butter.
We are trying to predict both the modes.
Yeah, so challenges is there for both, but we don't give much importance to that when you talk in terms of research. 90% of research is done on focus. We assume that there is more important. Because northeast monsoon is confined only to southern parts of the country, like Tamil Nadu, Andhra Pradesh, Kerala, and so that is very small place. So we assume that there is never a role. But nowadays the importance of October, so October to December rainfall also is increased. There's a lot of awareness is happening. The Tamil Nadu, the countries where the states like Tamil Nadu, Andhra Pradesh, Telangana, they are also very good. So there the agriculture, most of the agriculture is done. Okay, and this is at higher level is about 12 kilometers. Well, it is easterly, whereas in the lower level you can see some of the easterly winds. But if you go up, it's all. Yeah, so when it talks about monsoon season, monsoon current, then there's the analogy with the land sea breeze. Sea breeze, you must have heard about it. Sea breeze, the breeze coming from sea, and it will be a cool current. And what is the physical mechanism is almost same. You can see in the daytime land will be hot and the sea will be cold. So there is a temperature, there is a pressure gradient from sea to land. So there is a current coming from cold ocean to land warmer land, and it goes up. This is a so-called sea breeze and sea breeze. The night is just the base of it. So it is very prominent, especially in the eastern coast of India, from Chennai. They have a sea breeze effect. The importance of sea breeze is it modulates the temperature. So the warmer daytime temperatures will not be so high because there will be a sea breeze, cold sea breeze, and night also it will not be so cold because there will be a warm air. So this is the concept of the land sea breeze. Okay, and this is the same concept people try to do it for monsoon. So I told that monsoon is nothing but a perfect gradient difference between sea and sea and land. So air from sea is coming in from southern hemisphere comes up and towards north, and it gives a lot of rain. So they assume that the land sea breeze concept can apply to initial theories were all based on this. So this is the famous first theory came from 1686 as early as 1850. And his hypothesis, the main cause of annual cyclone circulation is basically the differential heating between land and sea, and caused by physical amount of the sun. So sun drives this temperature gradient. And Hanley in 1735 proposed that is okay, but then we will also take into account the Coriolis force, nothing but the rotation of the air. So that will create the southwesterly winds of the monsoon. In the very late recent years, Webster is proposed that moist process, for example, moisture content heating because of the cloud formation, cloud condensation, etc. will also be a third element in the monsoon. But this is the basic theory which started very long time back. Still, people talk about landscape contrast as the main driving force of monsoon. But many times this contrast theory may not really be applicable, and there's a lot of deviations of this theory. And one reason is so this is the theory which we've been talking about. The equator, for example, there's a lot of heating, so the air can go up, down, then come back. With the northern hemisphere, southern hemisphere also it happens. So this we call as a Halley circulation. One in northern hemisphere, one in southern, not Halley cell. And the same concept, the monsoon people they started talking about air from equator goes up, goes towards north, then goes up. This is the monsoon rainfall. Then goes returns back and comes down. Then again goes back. So it's basically a big circulation. And this is the monsoon circulation. And they assume that that is mainly because of the landscape. But really so I can keep this works. You can see how the different months the Halley circulation is getting changed into monsoon circulation. So in the winter months, there will be two circulations, one in northern hemisphere Halley circulation, southern hemisphere. The monsoon season is also big long monsoon circulation coming from southern hemisphere to northern hemisphere, goes up, comes down again. But the theory doesn't really work. If the temperature contrast is main important criteria, if the temperature is more over land, it should drive the more monsoon. The monsoon should be more. But if you really take the temperature over land and plot against monsoon rainfall, the temperature is more, we should expect more rainfall, but it's not. This is just negative. So when more temperature doesn't really drive the monsoon, so it can explain how the monsoon is coming, monsoon circulation, but it cannot explain the variability of monsoon. For example, 1 year monsoon is more, and that cannot explain the landscape. So there is a big objection by some elements, some researchers saying that this landscape component cannot be used to explain the variability of monsoon. It's not a really good example. So what exactly then monsoon is? How we can explain monsoon variability? It's a concept of morning. So a few weeks before Krishna was talking about so-called IPCC, the tropical convergence zone, is nothing but the air of the 2 airs coming down and converging, and the air will be going up and giving a lot of precipitation. So this is the red shows the northern hemisphere IPCC, the blue shows the southern hemisphere, where E minus P is positive. E is the evaporation, P is the precipitation exceeds surface evaporation. And so this is the area where the shaded area is where the precipitation is more than evaporation. So there are two areas where you can have large scale monsoon precipitation, the one area, and along still got nothing but excess. If you really want to see the target, like this, it's that long elongated clouds. Here, this is for southern hemisphere, and this is northern. Okay. And what happens is that this is the monsoon, so this is the precipitation, January and precipitation July. You can see the precipitation January was oriented east-west direction in the southern hemisphere, but in July it goes up. So there is a northward propagation of IPCC from winter to summer. And so that is very easily seen here in this also. Showing the few minutes back. This is the southern hemisphere IPCC, and this is the northern hemisphere. The interesting thing is this shift, northward shift, is not happening everywhere uniform. It happens more over the Asian region and also the African region and also the Australian region. But over the Pacific ocean, over the Atlantic ocean, this kind of northward propagation is not happening. So the northward movement of IPCC happens over the monsoon. So monsoon variability, monsoon can be expressed in terms of the northward propagation of and this theory, if you really follow, you can almost explain many aspects of monsoon variability more detail than if you are saying the landscape. And this is another example how we can do it. This IPCC position during December and January, but June, July goes up.
So how new is this hypothesis?
Hypothesis is last maybe 20-25 years. But still people talk about the landscape temperature contrast, and they still will talk about.
This is not something that is accepted. This new hypothesis.
New hypothesis also is there are a lot of questions. There are questions on how the monsoon is, monsoon variability, how monsoon variability can be explained.
We don't understand it very well.
Understanding, we know the how you interpret this. If you want to prove something, we can take landscape temperature contrast and prove it. If you want to prove something else, you can take this is it. That's what the researchers we do.
But this way of how things happen, that was forecast.
IPCC said this theory is not speculation based on observation. You know that it is moving, it's not moving uniformly everywhere. Most only a particular place where the monsoon is there. Okay, and this northward propagation of IPCC said, you really assume that the northward propagation can explain internal variability over why monsoon is from year to year. And also it can explain within the monsoon season there is a lot of variability. Some days it rains more, some days it rains less, so called acute cycle. Acute cycle also can be explained in terms of northward. So many known variability aspects of variability can be explained by IPCC, not by landscape temperature.
But can predict weather by this?
Yeah, that's what Krishna was saying. It's very difficult. Models are not really good of predicting the IPCC. And also in the intensity.
Some aspect is very, but there are
Yeah,
some
in
also-
general it predicts, but there could be a lot of changes. For example, in most of Indian models which are predicting monsoon variability, monsoon over Indian region, doesn't really keep the IPCC north as observed. Doesn't really move north. IPCC is more southern position than the observed position of IPCC. In the monsoon season, IPCC goes up to almost 20 degrees now, but the model isn't really good. The model IPCC is confined more to a southern latitude. So it rains more there, doesn't rain over northern parts. So I will show you a diagram. And so in the northern parts of the country, central India, India, the model predicts less rainfall than the south. IPCC doesn't go there. So it has a dry bias. Very common phenomena of all, you take any climate model. The dry bias is a very systematic. All the models predict dry bias.
It's not easy to fix the model now.
Fix the problem. It's a universal problem. Over Indian monsoon region, all the models predict less rainfall than others.
Slightly improved in the period 6.
Yeah, they will slightly improved. But still bias is very large. The number is very large. Okay, so I will move on. So this is the same thing. If you really plot the position where the IPCC is, what I saw, even April to October, you can see that it goes from southern hemisphere, 5 degrees south, 5 degrees north, it goes up. So it goes up to almost 20 degrees. This is over the Indian region. And if you really plot the rainfall also, beautifully it goes up. You can see that it's going up in that May. Then stays there, there's a monsoon season, the story comes. So this northward propagation of IPCC can explain many aspects of monsoon. And so we have a new concept of global monsoon. The monsoon can be defined in a global perspective. So there's a definition of global monsoon is the summer minus winter precipitation exceeding 2.5 millimeters per day. And 50%, 55% of the rainfall should happen during the annual rainfall should happen. If we put these two conditions, these are the monsoon region we are getting. We have we call South Asian monsoon where you have India, Pakistan, Bhutan, Nepal, to some extent Bangladesh, and we have an East Asian monsoon, and we have a North African monsoon, and we have South African monsoon, we have an Australian monsoon, over America we have North American monsoon and South American monsoon. Out of this, North American monsoon, South American monsoon is not well researched, it's a new concept, whereas the Asian monsoon, especially South Asian monsoon, is well researched, thousands of papers, to some extent North African monsoon, and also Australian. And among all the monsoons, South Asian monsoon is probably the strongest monsoon, and also it is the monsoon where the predictability is pretty compared to all the. So North American monsoon, North African monsoon is far better than any other monsoon where we can predict. Africans are pretty that we can predict better. Okay. So this is a mean rainfall pattern, looks like monsoon season, it is a beautiful. And we have a strong monsoon rainfall, heavy rainfall along the west coast, and also we have a lot of rain, heavy rains over northeast region. And over, if we go from here to here, the rainfall decreases. Then when we go from here to here, also decreases. And this is a place where the southeast of Tamil Nadu, the rainfall is almost same as Rajasthan during monsoon season. And also, you can see that Nepal, they get a lot of rain. Pakistan, they have monsoon, they also get monsoon rainfall, but the rainfall is less. Bangladesh also get a good amount of rainfall. And this is just nothing but the coefficient of variation. You can see that over the west coast, the coefficient of variation is very small, but when you go over Rajasthan, the variability can be even up to 3%. Very heavy. Okay. So if you take monsoon region and take an average of monthly rainfall, it's like this. Get rain from July, August, September, and this one is a coefficient. Reduce as coefficient of variance comes around 20, maybe 10 to 20% during monsoon season, but the other season very different. But the amount is also very. And this is the rain plots, the beautiful plot. We can do that. You must have heard about in literature, what's called rainy day. The day in which it rains. Okay. After 122 days, it doesn't rain every day. And so IIT has a definition of rainy day. If rainfall 24 minutes, 2.5 minutes. So if you really want to see the spatial map, we have a lot of rainy days over the coast. So there it rains almost every day. Okay. And also over the. But over Rajasthan and from the amount of the number of days is less than 20. Okay. And this is the region where this is the part which shows the heavy rainfall. Some days there is 5 mm, some days there is 10 mm, some days there is 65 mm more. The IMD definition of heavy rainfall is rainfall is more than 65 mm. So this is a special pattern where it rains only over along the west coast. The heavy rains are talking about, and also the parts of India and also northeast. Also the foothills of Himalaya. The foothills of Himalaya is a place where heavy rainfall is very high. People really normally don't give attention unless there is some flood happens, some people die. Otherwise, it's a biologically that is the region where you get a lot of rain. Okay, so now the basic question. I told you after 122 days, it doesn't rain every day. And also in when it rains, it doesn't rain 24 hours. So you know how many hours it rains? Over 122 to 24 hours. That was the first work I had done in meteorology when I was in Nowcasting office. A person like Precipitation, I don't know, they know him. I don't know. I went and talked to him and Precipitation fresh from IMD, first joined IMD school. And then talked to him, he's the beast of the meteorology in the country. So I went and talked to him, I want to do this. He said, because we are on the test, you do what you want to do. So, from Miami, I don't know much about it. You do analysis on rainfall. Do you really want to count number of rain cases in this country? Very sarcastic question. Then he asked me, you know, how many hours it rains in Ahmedabad? Then went back and found out. There is a seasonal rainfall is 79 centimeters, almost 80 centimeters. There is IMD takes, IMD has observatory or rain gauges for self-recording. Automatically record. Continuous rain gauge, continuous observation. So you can count how many hours it rains. Surprisingly, it rains only 120 hours. That means 122 into 24 hours, it rains only 120 hours. And half of the rainfall, that is 40 centimeter rains in 16 hours. So that is the calculation. Many people don't know. Many people don't know. Characteristics of monsoon rainfall in India, this is the characteristic. You take any station, this characteristic is same. Only thing that 120 hours, if you go to a place like Bombay, it will be 300. It rains more number of hours. But half of the rainfall, it comes in a small number of hours. Okay, so this is a spatial map which we prepared using IMD. You can see that along the west coast number of hours is more, and over northeast also there is more hours. But if you really see the how many total rain hours for 50% of rainfall. So the important implication of this aspect is when it rains in a few hours, it rains in very heavy amount. And that amount of rainfall is so it rains in 1 hour, it rains in 10 centimeters. So it simply goes up. And remaining is small millimeter, 2 millimeter, 3 millimeter, adds to the season rain. So that's what they say at that time. Rainfall which comes in shorter period simply flows off and is not available for you to store. And remaining water comes in a 2 millimeter, 3 millimeter, and before it comes to the ground, it evaporates. So unless you have something to store the water, conservation of water, you cannot really manage. So that's why he was giving an example at that time. Gujarat, Kazakhstan, they have wells, they have a pond. In every village they have a pond. Maybe because the water which comes here, they don't allow the water to flow out. Water is available every time. Our modern water management people don't know about it. And that's why even Cherrapunji, it gives a lot of rain. After the monsoon season is over, they say there is no water. We don't allow water to be stored. It's just an example. Okay, and now the question is, what kind of clouds really give rain? So in meteorology, we have different, clouds in three different categories, depending upon where the clouds form. These are all low-level clouds. It starts from the base will be at the low level, but it grows. And these are all middle-level clouds, or these are alto clouds. And cirrus clouds in the top. It's around 10 kilometers. You must have seen every day. It's kind of cirrus cloud. So in that, this cloud doesn't give any rain. Only the clouds here and here from give. And there are clouds called cumulus and cumulus clouds, which are convective clouds, which give plenty of rain. Cumulus cloud is nothing but a thunderstorm. So we have different category. People a trained observer of IMD can really differentiate what kind of cloud. So now question is how much of monsoon rainfall comes from this cloud? So what's the criteria? Well, interesting question, but I don't know. But it's all came from Roman names, all Roman names. There are very low-level clouds which can give a lot of things. And so this is all from satellite data. We can from satellite you can differentiate different type of clouds. And this is the cloud fraction from May to October. You can see that the monsoon season, June, July, August, you can see that the cloud factor is almost 95%. It's a lot of cloud, then slowly it comes down. And this is the deep convective cloud. Deep convective cloud means the cloud which can go up to 10-12 kilometer height. So also it has large optical depth. And you can see that the more wave number large optical depth. And if you really plot this map as a global map, you will see the maximum cloud deep convective cloud. Bay of Bengal is a region where you get maximum. And these are a very complex system, Understanding of the deep convective clouds is not well known. We have a lot of gray areas, and these clouds play an important role in monsoon survey. And this is the, so as I said that different types of cloud will give different types of rains. Convective clouds will give a heavy rain, whereas stratiform gives clouds will not give that kind of heavy rain, but it gives a lot of rains. Okay, and shallow rain doesn't give much rain, it gives only very little. So these are the different kinds of rainfall patterns. It's also taken from study from using satellite. It's called trim satellite, and you can say. So this is the region where you have maximum convection. So your area or this area is more prone for convective type of. During my time, during monsoons, Pakistan. So maximum type of maximum rainfall, seasonal rainfall comes from convective over this region. And whereas in especially over central India, maximum comes at the top. Shallow rain from over this close. So this is the way we classify what kind of clouds are and what kind of different kinds of clouds are.
How good are satellite images picking up different types of clouds and numbers they have?
You mean this classification? This classification is done very well. So because I have radar, trim satellite has a cloud radar and differentiate between two different types of clouds depending upon the perspective. That's a common cloud water content. The satellite which this picture is drawn is the satellite called TRIM, Tropical Rainfall Measurement Vision. And that radar satellite has a radar looking downwards. And the radar can detect the different types of clouds.
That's probably useful then for casting the rainfall.
No, it's not used. It's only for understanding the basic concept. Not only the climate concept. So it's not used for forecasting. But TRIM also gives a lot of rainfall data. The wind data is very famous. The rainfall data is very famous. Now the TRIM satellite is right. They are being replaced by something called GPM, Global Precipitation Mission. How many of you have seen the film Sunday by Auroop? Sunday by Auroop. There you are thrown as a NASA engineer. There you are thrown as a chief scientist of GPM. Really see. So now GPM the satellite has come out.
Ramesh Kakkar.
Ramesh
Kakkar. He played the role of Ramesh Kakkar.
He is a friend now.
Looks like satellite has a radar.
GPM also friend. The same kind of thing. He has a little more accuracy. So the data is available every day. And in IMD, IMD and IAG together, they make this data set along with the IMD linkage data. And they merge it and they produce genetic kilometers with data. And it's available free of cost. It's available on.
So, 25 kilometers more data.
Rainfall data. So data from GPM and GPM data available next day. Today's data will be available next day. And so the IMD use of that data, plus the rain-gauge data, observed rain-gauge data, we have about 3,800 stations reporting every day. Rainfall. 3,800.
3,800 was no rainfall, but for interpolation, you use satellite.
No. So they merge it. So they do an objective analysis as a first guess is the IMD rain-gauge data. And satellite data will add to more. And it's a global product. So that means whatever land is there engages, but whatever ocean is being used.
But that used to be
Of course, it is not used for forecast. Of course, you can use it, but the models cannot use it. Model can use it for validation. For some, if you want to reduce the forecast, if you want verify verification process, but you can use an input for your MLR. 25 kilometers. Right? It is freely available. As I said that in the morning, I said that now they are also working on merging the radar data. So there will be rain gauge, satellite. Kamal Jyoti, who is coming tomorrow, is working on. Okay. So now there comes monsoon variability. We have variability in different types. Diurnal means within 24 hours, there is a lot of variation. And synoptic means after 3 to 4 days, that's mainly caused by weather system and the system. Intra-seasonal is very important component. And year-to-year variation, where monsoon seasonal forecast becomes important. And even we have multi-decadal. So monsoon varies in different time scales. And because it varies in different time scales, we have a lot of idea about developing models, predicting, verifying, proving. Krishna is more focusing on intra-annual to multi-decadal kind of thing aspects. So there's some people who are industries and some people who are So I will mention before I start this. So if you really think rainfall anomalies or solar wind at 1.5 kilometer, do a kind of spectral analysis, we get peaks somewhere 3 to 4 days, 3 to 5 days, and then 10 to 20 days. 20 to 20 days, then also you have cycle about 30 to 60 days. So these are the different phase of periodicity. 3 to 5 days really comes from synoptic, basically it's not weather. The weather system forms with persists for 3 to 5 days and goes out. Then again another system form of 3 days. Then also then intra-system time scale we have 10 to 20 days to 30 to 50 days time scale. So this intra-system time scale both is well established and not about content. So I will speak about diurnal variation. Okay, not very clearly seen. Okay, so I will. This is the so if you really take earlier report data, do a harmonic analysis. You can differentiate between amplitude, you can calculate amplitude, you can calculate the phase, and also the ratio you can calculate. And if you really calculate the phase is the time at which the maximum rainfall is. Okay, and look, this looks like, and this is number of this is the standard time, local time. And you can see that over northern parts of the country, it is around 12 to 18 in the evening. Late afternoon or evening is the time where you get maximum rainfall in a day. Okay, this is climatology. On a particular day, it can rain in the morning, but if you take a long-term data and do this harmonic analysis, you get like this. So most of the so basically it's called convective rain. Daytime temperature goes up, heats up, it is producing convergence, and the air goes up, it is runoff. So that's basics here.
And not at night, but well,
Yeah, it can rain at even 12 o'clock and 3 o'clock. But you should expect monsoon season. Expect over this region, you should expect rains to come. More rain. That's the meaning. There's a lot of importance, there's a lot of value. And over the very interesting thing is over the foothills of Himalayas, it's very morning. Foothills of Himalayas, for example, there are then I get the rain in the early morning. Rain means maximum rain happens. Why it will happen? Because the daytime, nighttime, there is a wind called adiabatic wind. The winds coming from the hills to down, and that is coming down. And also there is always a monsoon flow here. They mess together. Either a plane ascending motion, connected rains, and followed by convective. And so that's the physics behind the early morning peak there. So it is not uniformly distributed. It's some important thing. It varies somewhere here. It is the late night over southern peninsula. Over here it's all afternoon. It varies from different times. So we know to some extent we know what is the physics behind. The next, so you can also see the next picture. You can see this is the average. This is again from data. You can see that from the morning, early morning, somewhere is the maximum over here. But over the India, over Central India, you see that just 9 to 12 UTC is maximum. 9 UTC means the afternoon 4:30, and this time slowly it decreases. Peaks are somewhere in the. Okay, so this is a diurnal variation. That's number one. So then the question is whether the model really picks up this diurnal variation. Answer is no. The model has serious problem of picking up diurnal variation. So one of the challenging problem of the present day numerical information model is models are not good in predicting weather. I told that the morning, the afternoon around 2:30, 3 o'clock, for picks up the Central India, the model it picks up early. It starts picking up the spectral low. So there's a phase difference between almost 2 to 3 hours in the month. The question is how you fix it. The model tries to understand the conversion is starting much earlier than what is released.
Then IMD making how many predictions? It's kind of it's using those models and maybe not using them.
But understand prediction, you should first of all tell thunderstorm is going to come, number one. Number two, people will ask me when is going to come. That second question. Third is how is the intensity? Whether it is small thunderstorm or big thunderstorm. So models will be able to say that thunderstorm is going to happen. Basic question is when it's going to come. The model, if you really go with the numerical representation model picks up thunderstorm much earlier than what. And we give prediction saying that by model thunderstorm will not. Thunderstorm will come much later. And also there's a problem of predicting the severity of. A small thunderstorm will not cause very enough damage, but a severe thunderstorm can range of rains. Number two is heavy, strong winds. Important thing. So this is a basic problem of model using models for predicting thunderstorms. The model you are saying that ML is a beautiful replacement. Okay. So then I will synoptic scale delivery. So as I said the morning, sorry, Krishna was talking about the different weather systems, the classic monsoon rainfall. And so one is the monsoon depression forms or variable node and moves across the line that gives a range of rains, and monsoon depression is important. The synoptic weather system in the and these are for different marks. You can see that this is for India. India is the way. I have India here. Okay. So this is the you can see the monsoon lowest form here in moving here. For this is always go for many reasons, many reacts. And this is for July, this is for August, this is for September. Very interesting point of the rule of soil moisture. Whether soil is moist or not. Very important. You can see the difference between cracks in June. It moves only up to here. Most of the depression forming in June, it dies somewhere here. It doesn't go beyond that. Whether it dissipates. But by July, it goes up even up to that. The basic physics behind it is soil. So June, soil moisture here is very dry. Because it is not rain. It is not rain. So soil moisture is very dry. So monsoon depression cannot be like in ocean, tropical cyclone. Ocean is very important. Ocean gives a lot of energy to cyclone. So that's why when cyclone comes and falls over the land, it really dissipates. Because the ocean energy is cut off. This is basically petrol. It gives a lot of energy in terms of moist length. The same physics goes for monsoon. Monsoon depression is a soil. Soil moisture, like ocean, the tropical cyclone, ocean, for monsoon depression is soil. Soil moisture observations, predicting, putting it in the weather model, etc. is very important. It's very beautifully seen the importance of soil. Okay, and this is the fraction of how much rainfall will cause due to monsoon depression. Here, the intra-season variability, I told that you can do that 10 to 20 days and 30 to 60 days. There are two cycles. So this is the beautiful. We really thought the kind of speed or home weather diagram, and nothing but the movement of northward movement of convective clouds. You can see that beautiful northward propagation at different time scales. So it's separated by almost 30 to 60 days. Process oscillation. And then we have a concept of active and phase cycle. So in monsoon season, some days it rains more, some days it doesn't rain. So we have, if we take an area from here is called monsoon core zone, and we plot a average rainfall, it looks like this. But if you plot it in anomalies for different same days for different anomalies for you can see that there are some days in which the monsoon rainfall is more over this region, over this spot, and some days monsoon rainfall is suppressed, again more, again suppressed, again. So the top we call active. And we have a clear definition with less than -1 standard deviation is called break, and more than 1 standard deviation. So active break phases of monsoon is very, very important. People are trying to understand why it is happening. Number one, can we predict? So if we can predict it, how Yearly we can trade. 10 days time scale, 5 days time scale. Because for farmers, this cycle is very important. For example, a break is happening. Now he will be asking when it will rain again. Isn't it? Because he has to continue his farming now. So if he can tell that now the break is there, you will continue for the next 5 days. After which you will get again and do that. We can tell almost 2 weeks before. Okay. Similarly, if active is happening, and if we can tell this active monsoon period is happening, continue for another 5 days. But after which there will be a break spell about 10 days. Then we will be. These are the important information which farmers are looking. So that aspect I will come later. Last presentation I will tell how good we are. And if you really see the clouding pattern, it looks like during break, most of the clouding is close to hills on Himalaya. This is a typical cloud over during monsoon season, during active days of monsoon season. You can see there are a lot of clouds. And if you really see the OLR composites, beautifully, you see this opposite. This is the break spell composite, where the conversion is completely stopped, but the conversion will be enhanced or that. But the active period conversion is happening somewhere. You can see this extending even up to Precipitation. Beautiful scene, beautifully you can see the low, negative OLR anomalies, but the Indian Ocean is fast. So when convection is more over the Indian region, in Central Asia, convection will be suppressed over the Egypt. Just opposite. And seasonal variability is important. This is if you take 122 days of rainfall and averaging, will be one value. So monsoon season it is about the average is about 86 centimeters of monsoon rainfall. If you take all points of the Indian country, take an seasonal rate. If you take all the remaining seasons, it comes around 110 centimeters of our country. That means, what do you mean by 110 centimeters? Are we assuming that 110 centimeters is 1 meter? Assume that we have 1 centimeter. That means from January to December, whatever rain comes, assume that it doesn't go out, doesn't evaporate. At the end of 31st December, you will get 1 meter of water spread over the whole country. So you can just visualize how much water we receive. Multiplied by the area, 1 meter multiplied by the total area of the country, that will be cubic meter. How much water we get? We get plenty of water. As I told in the beginning, we are fortunate that we have.
How is that benchmark with the rest of the world?
What do you mean?
If you look at landscape all over the world, all the rainfall, how much half a meter?
I don't know, global average, I don't know. Of course, monsoon season gives a lot of rain. Much more than global average. Of course. Amazon gets more. Amazon gets more. But if you take whole globe, because there is a lot of deserts, so average will come down. And the question is, this rainfall doesn't really stop it. Every year will not get 80%. Some years you get more, some years you get less. So then these are the years you call it the drought. Some years you become drought, some years you get monsoon. So the question is whether can you predict this very? This is called seasonal variability. So that is the question. So I will be answering this question later. And this has a lot of impact in the Indian economy. So there's a beautiful plot, which is, I am not sure this is plotted in 2006. I am not sure on the recent plot how it looks like. This is the percentage difference of monsoon rainfall. And this is the impact of Indian GDP. It has a huge impact. You can see that when the monsoon rainfall is low, have big impact on Indian GDP. Okay, but it's in the positive side, even if it's a big rain, it doesn't really give that kind of impact to GDP. It's not a very linear one, non-linear one, and it's not uniform. The positive rainfall will not really have a big impact on GDP. The question is why? But negative impacts are a drought really can pull down the. So it's mainly contributed by. So I will stop here. I think when I talk about next is the decadal value prices. That if you really plot a 31 running mean black line, you see that there are rows in which low, then more, then we have a lot statistical variability of 10-year times. Question is why it is happening. And question me, the next question can be. I will start here. This is the probably last slide. So, and this one new technique, I thought I will inform you about this technique. It's called ensemble, complete ensemble, include complete ensemble empirical motive composition. So you do technique where you can have time series in decompose different components. Now, I know there is spectral analysis, but it's more efficient. Start here. Yeah. Right. You don't get, if you even if you have, you don't get. The quality of data is much. This is good. You like they're happy to be. That is what. But you are a how is it how is it how data. I talk you. That's
short answer.
Yes.
You just taking questions to begin with.
Yeah, sure.
Because I think you say that in.
Yeah, sure.
You can just, yeah.
1 minute. Yeah. Can you start the second?
This is how you define. This is for the internet topic. Convergence. So in the, if you really see the wind pattern over the topic, the northern hemisphere is all northeast. And southern hemisphere is all southeast. Some place, somewhere we converge. That line, it's a line where you get a lot of scale convergence, large scale ascending motion, and a lot of scale. The range is basically maximum cloud only. So that's where place where it's right. And that is the region where all documents are from. So a small line is a line. It moves upwards, sometimes it goes down. Southern the winter season for our winter goes down. The summer season goes up, and over the monsoon region it comes and we call it summer. Pacific also it goes down. But it's not the Atlantic, it doesn't go down. It is almost like a state. And this is where ITCs, the all tropical cyclones forms in the ITC. A small vortex forms there. Then it moves, it will get intensified through some mechanism, what we call instability mechanism, and it goes. Yes,
when you're having this connection,
yeah, there's a region, I saw we got ITC the region, I think, but east west radiation of the convergence goes. And tropical cyclones form the vortex must be formed. It gets intensified through mechanism, different instability mechanisms. Once it goes, then it goes beyond the very next to very. Then it moves now. Gets a dissociated with IBC. IBC will stay there. This one no will stop.
So, what is going to happen there at every point, no matter the so, why are the important things that we're talking about, hypers are forming in the top? Why are I think the mathematics theorem that there must be about it somewhere. If the why did they preferentially form that region?
Preferably forming over the, that's the region of convergence. So yeah, what that can form only over that. And one height is moves north and south. You need a sphere, you need a sphere to rotate. You need a particular color that can be trigger a vortex over which we can. And it forms of the equator, it doesn't form near the equator. I show that IDC said one is the southern hemisphere, one is the northern hemisphere. You would have noticed that equator is full of free of any cloud. So the cyclone cannot form over the equator. It is because the Fourier response is zero. You need a Fourier response to rotate. So Fourier is nothing but 2 omega. Fourier response is nothing but 2 omega sin phi. Omega is the rotation. 2 omega sin phi. Sin phi is 0 there. Sin phi is 0, so you get input. Also, you start somewhere around 10 degrees now. So, Fourier response is a major factor to trigger the vortex. Okay. Go to the next one. So, this is a part 2. So question is, many people talk about the weather and climate are kind of a same bag. It's not so. Climate is different. And so weather is instantaneous what you experience. Climate is a kind of a long-term way. So basically, climate is what you expect, but what you get is weather. Weather is what you. So for example, Bangalore is climatologically, climate-wise is good. And particularly, weather can be very nasty. It can give like flooding and all. So the question is how you predict. So how you predict? There are many ways you can. I'll start with persistent climatology. Today's temperature is 25. Assume that tomorrow also it will. That's the one way of it. Okay. And so persistence for temperature it works very well. But it doesn't vary that kind of. It doesn't have that kind of variation. Climatology is not used for temperature. It can be used for rain. For example, you can say that lower sodium next monsoon season can get the same amount of climatology. For example, temperature can be.
See on the.
Yeah. So the second is unlock. For example, a particular event has happened. Next day, so like for example, a person the payment, they gave a lot of victory. So for the forecaster, you can find out some kind of business situation in the past, situation. And when those situations were met, what was the rainfall? Really, what was the rainfall? You can find out the similarities from the past data and try to predict it. Unfortunately, the analog doesn't really work right. Because when the same scenario is setting, you can get two different results depending upon. So it's highly non-linear. Weather and precipitation is highly non-linear. Even though you may have same kind of situation, but the highly correlated. Some people use it analog way, but not really. Only another is the climate series. If you assume that there's a beautiful cycle, 2-year cycle or 3-year cycle. Possibility and ecology, weather and climate, we don't have a cycle. If we had a cycle, we would have missing people. So, but we don't have. Then the third is classical method. We use extensively certain, especially for seasonal forecasting. I will be talking about that. The dynamic method is the most powerful. In all exceptionally used, very powerful and improved substantially. Still, there are some gray areas. And the latest emerging area is the area.
There are cycles. Also, these are cycles. There are cycles. So there are cycles. So the phenomenon is like monsoons come roughly at the same time. You won't capture the positive fluctuation, but at least there is some information in the cycle.
So I'll tell you, because maybe some people ask me what do you know, how good you are. I normally as a lighter mood reader, again I know who will come by. It will go where. This is well known. This idea is people. So we can tell monsoon is coming, monsoon is going, but even monsoon coming, answer you say. There can be there's a lot of variation. So almost 10 days of 50 days. It can come on 1st June, it can come on 26th May, it can come on 10th of July, it can even come on some latest starts at 18 June. Then it comes 18 June. Almost 18 days of. So even though we know monsoon is going to come, what we know very, very confidently say monsoon will come. We are very confident. Will come and go. But beyond that, I think there's a lot of. Okay, so question of forecasting. Different kinds of forecasting. We start from nowcasting, and that means basically forecasting next few hours, what will happen next few hours. Basically, it is used for thunderstorm, lightning, flash flood. We also have a small range, for very short range, hours to 1 day. And then that also again thunderstorm, lightning, flash flood. Short to medium range forecast is the main method used for, especially for informing people in agriculture, water resource management. For them, the forecast up to 10 days is very important, 8 to 10 days. So basically, we use to forecast of rainfall, tropical cyclone, heat and cold waves, rainfall. Yeah. And then extended range forecast is a new emerging area where we are doing a lot of research. Where we can predict next 10 to 30 days. It's the period where we want to forecast. It's basically actual base cases just about it. And this is essentially used for farmers. And then the season up to one season before, monsoon rainfall and El Nino, prediction comes on the seasonal prediction. There's also a new emerging area which I think annual weekend. Probably the climate change prediction which are talking about 2070 what will happen. 2100 got. That's what I think. What is the use of saying by 2100 monsoon will be like this or heavy rainfall will be like this? No, practically, if I say that even for adaptation, 2100 is too far. Too far. What the government for Odisha, for Narendra Modi, Prime Minister, Honorable Prime Minister, he will happen after 2 years. Yeah, he can take a decision. We can, in terms of economic policy, in terms of development policy, investment, If we tell them that after 3 or 2 years and up to 5 years, monsoon rainfall is going to be very bad. We'll have 2-3 droughts. very useful information for him. Isn't it? So that's a new area with the next few 1 year to 10 years. So that's a emerging area. Climate change needs to so very important. This is very important information. In a weather system, different weather system have different spatial types, spatial scale as well as temporal scale. For example, dust level will have a small spatial depth, 10 feet. Okay, a tornado will have 100 meters, and cumulus cloud will have 100 meters. From mesocyclone will have cyclone thunderstorm, severe thunderstorm will have cycle, sea breeze will breeze. So you can have different times, the different tsunamis between the system have different speeds. And the time scale also goes back. For example, dust level is a few minutes, last for a few minutes. Thunderstorm for some it will be a few hours. It will have the thunderstorm forms, it will dissipate in a few hours. Whereas tropical cyclone will last 1,000 kilometers, and it can last about few days. Short, it can even go up to 1 week to 10 days. So if the spatial dimension is more, the temporal dimension is not so this. Okay. Then question comes, to understand the spatial and temporal dimension, you can also predict different ways. For example, a tropical cycle, dust level, you cannot predict in 1 week before or 10 days. You cannot. The time span is even thunderstorm. This is a small dimension, both temporally as well as. So you cannot predict in 1 week. The cyclone you can predict. Monsoon is a broad. Monsoon is a planetary scale, 10,000 of kilometers. So that you can predict even 1 season. So that's why many people ask, can you predict Onipet weather? For example, what will happen on 12th of December on the whole Onipet? Can you tell now? Answer is cannot. People tell, still people, model can give you answer, but there is no predictability, no value. You cannot give it. So, but you can tell December, there is a probability of 4 normal temperature over 20%. That you can. But exactly, 23 degree or 12 degree. So this differentiation you should always keep in mind. Once you try to predict it, you should know what you are predicting, what is the spatial dimension, what is. So depending upon the nature of forecast, the models which you use also will be different. The models which you are using for tropical cyclone cannot be used for models for thunderstorm. Predicting thunderstorm. So this differentiation is very, very important. If you really want to do forecast, if you want to just listen to the forecast, then it's fine. If you really want to do forecast, then and so these are our forecasts. The forecasts are given in different time scale. It starts from minutes. You can just like a few minutes. You can start an hour, days, 1 week, 2 weeks, 3 weeks, season, years, decades. So it has a different application. The forecast in 1 week will have different application. And what it is used, what forecast value. If it is a few hours, you will say watches. We can also use for threat assessment. If it is a long time, we can use the outlook. So monsoon prediction we call as a monsoon outlook. For example, what will happen for going monsoon season. So it is given to the government to understand that what is going to happen. We can outlook. Exactly, it may not really happen, but it will have a broader idea. So the forecast applications also different. And also how it is used for. So in the morning again, so those of you are asking about what's the role of oceans. So this is a time scale for different aspects of a system. Atmosphere can have a memory only of 2 days. So if you really want to predict a 1 month, atmosphere will not have. Because after a few days, atmosphere will forget what is where it starts. Okay. But if you want to predict for the next 5 days, 6 days, atmosphere will come. Ocean doesn't have a break. So you need not have a coupled month. You need only atmosphere. But if you want to predict it season time scale, for example, next 1 season, ocean becomes very important. The ocean, the day-to-day time scale, the ocean doesn't really change. Temperature of 25 degrees, more often, but over land, over atmosphere, they can change from one place. So the variable, day-to-day variability of atmosphere is very high, but it has a memory only up to. So if you want to predict a longer time scale, you need it. And some people use a mixed layer of 100 meter also, some people use deep ocean, going up to 4,500 meters, but nowadays all coupled models have very deep ocean.
Are we getting good data from ocean? No.
Not good as atmosphere. Not good as.
They are using happy.
New instrument of MOS cannot Auroop. We send balloon, many people say that in our lab we send balloons and take observations and deep. Similarly, for atmosphere, for ocean, it's temperature and salinity. That will be salinity. How much salt to come? That's very important. So salt content, that is salinity plays important role of oceans of place. Take a density in the atmosphere. Salinity plays important. So it's a flow. It goes down up to 1 kilometer and comes back.
It's not taking the.
Yeah, while going down, it takes observation.
So floating in the.
It is a floating. Goes down, then after reaching 1 kilometer, it goes up, comes up.
How many we have?
We have whole Indian Ocean, we have put more than 300 now.
This is what we have.
But it has a lifetime of 50 days. Today's days. Very costly. And it's not made in India. We import it.
It will be eaten in India.
All the ocean basis.
All the food.
All the whole. We do not specify the area where we. So, and also we have fixed bed of weeds. So this is almost like anchored. Then we have got drifting boards. Simply you put it there, it goes on drifting the ocean current, and wherever it goes, it takes observation and send it to sunlight and stuff. So the new revolution is actually Auroop. If you not important. So what ocean we hold not only temperature, we also need the vertical profile. Like atmosphere, we need a vertical profile. We also need to know the Auroop folks came the skill of muscles, that's why ocean forecast and but India is responsible for Indian Ocean, but all other countries are putting. So the whole topic, I don't have a map to show you, but I can find out if you want. So beautiful data. The ocean data is getting increasing a lot and taking a lot of resolution.
We have enough information. People
so this only goes only but it's still new. And satellite unfortunately cannot see beyond the surface scale. Satellite can measure only the scale. Ocean is very, very peculiar. The electromagnetic wave doesn't propagate. So if you really want any measurement, it's like use acoustics. Acoustic sound waves. Electromagnetic wave doesn't. For example, light, it goes beyond 10 meters. Whether atmosphere you can use microwave, different kinds of electromagnetic spectrum you can, but in the ocean you cannot. Unfortunately. So we use for everything we use acoustic. The investments are very high. Ocean investment are very high.
You don't put like a station or something inside.
That's why I said there are data we use some fixed location. It's a tied to the surface. Right? Surface, it doesn't go. So we have about 18 of
Yeah, recently they've been around.
no, they have been around for last 18. The institute in Hyderabad. So if you really want to go for years together, then you do it. If you want maybe 1,000 years, you need time. So different kinds of model, as I said, we have a turbulence model, it's called log scale ND model. But as which always we don't use it. We start from Nowcasting model, so 1 kilometer. We have a mesoscale model, a model called WR of weather and forecasting. It's a very popular model and it's freely available. Everybody can download it. Not only that, it's beautiful model. Global atmospheric models. So what I said is that if you really want to predict a longer time scale, if you want to predict a bigger system, you need a global model. you cannot use the regional model. Okay, but if you want to predict only thunderstorm, heavy rains, heat waves, etc., you can. So, but for climate change scale, you need coupled rules number model than Krishna was talking about this. So final, so where we use it for climate change. And this is a very different kinds of models, grid size, and time, model domain size, etc. So as I said, that Krishna was the numerical prediction started from Richardson, and he used many people to solve the equation. And as I said, he did not figure out the sound waves and wave waves. So his calculations, he spent about 6 hours. 6 hour prediction he made with so many people involved, and the focus was so bad. So because we did not figure out. And he assumed that future, he never thought about computing. He thought that in future there can be big factories using level forecast. So this is a cartoon which many people paid what Richardson thought about this. But he thought it is the prediction is possible. And this is basically this person. Julie Vigaranchane, he was in MIT. He is the person who really the first paper. It's the first paper on numerical prediction. First was published in the Journal of Failures in 1950, 10 years before I was born. And this is the equation is solved. It's basically barotropic vorticity. Vorticity. And you must have heard about this one Newman. So he used a computer called NIA, and this computer is completing 7 years. And it was able to do 5,000 additions per second. 5,000 additions. Now it is in beta, and people are talking about even XR scale, then more with 80, 30, 80. And this is a latest modern supercomputer. We use it in countries. IITM was directed the top of about 10. And now they are upgrading in 24 now. And this is how the enabling system works. You start from data. You need so NWB is nothing but initial value. Initial value initial data and run the equations. Basically, it's a different equation. Solve it. Integrate it with forward path. That's the basic fundamental principle of NWB. So whether it is for weather prediction or even for climate prediction, the concept is.
But does the world follow this? Well, I think that the planet, if the initial conditions were known to be, I know how the planet follows, will it be more
No, you have the initial conditions of the three-dimensional
actual planet. If I knew the initial conditions, will I know how the planet's weather will or will it be forecasted with the real world?
We can predict it using the equations, fundamental equations.
But will the real world be that?
Yes, it should be. It should be. They definitely should be. Because we use the equations of conservation of mass, energy, and the momentum. Yeah, the basic principle. The same principles are used for astronomy people. For example, they will say after 1,000 years, this star will move from here to here. A meteor will come from here to here. How they predict it? It's the same physical system. What is the our atmospheric physical systems are covered. It's a code.
Now, people try to avoid also in models.
Yes. Uncertainty you cannot introduce it, but in models of the because initial conditions are not. Whatever observations you take, initial conditions are not perfect. Okay. So the error in the initial, I will talk about that. The initial conditions have an error. That error will go on going.
Only stochastic is the
Usually, because there is a partial differential equation, you can solve it only if you know the t is equal to 0.
No, but what you're saying is that partial differential equation guide the world better than stochastic.
We know that these equations wrote at theory. So short-term prediction is okay, but maybe longer term may be problematic.
So I will tell you, so for longer time, what we do, we don't use determinism. We use again stochastic. We prepare using the same equation. We prepare a scenario of we call example different scenarios. From different scenarios, you can calculate how much probability.
But then it's okay.
Stochastic comes under
Under the initial.
yes,
Ensemble initial.
yes, only we do in something, the initial conditions are not perfect. So to take care of the uncertainty in the initial conditions, we prefer the initial conditions given there. For example, temperature is about 12.5. Can be 12.56, can be 12.48. Okay, small error. And the small error is good enough for giving uncertainty in the forecast. So we prefer the initial conditions. There are many ways of preservation. Methods I've taught. And so we present initial conditions, you prepare many forecasts. So if you have a big computer, you can run hundreds of it. What we do now is 20, sometimes 40. So once you have an example forecast, then you can prepare basic forecast.
But the fact is that the ensemble will stabilize in progressive test. It's not going to be like 1,000.
Yes, yeah. Okay, how many examples you need? How many example numbers you need a perfect?
So it's not like 1,000 I get 1 answer, 10,000 I get a 3 different answers. It's not that, right? Yeah, it's always
Okay, right, move on. So you start from an initial condition, then you have a model. Model has assimilation, then it's a part of dynamics part. And then when dynamics has about equations, then you have physics. You can post processing. The post processing also nowadays many ML methods are being used. For example, model doesn't give you a thermostat in the model. Model gives you temperature, humidity, speed of system. You have to convert it into a forecast of thermostat. Okay, so a good forecaster who has a lot of experience can, by seeing these parameters, but it may not be an objective way of it. If you really want to do it, you can use this forecast, model forecast to predict a thermostat. So ML methods are essentially used for post processing. The post processing of the model output. So the forecaster in IoT don't use the raw interpretive forecast for issue. Okay. Either they apply their own knowledge that comes with the experience, or they use this kind of method. Okay, so now where are the data? How you get the data? These are the data. You have plenty of data. So we have satellites, that is also you have polarizing satellites, you have geostationary satellites, and you have IR to research aircraft you are talking about, even commercial aircraft you have LVFI, biological imaging observation, that's why instruments from temperature everything. And that data observation goes into your office on relay mode. And also we have chips, wherever chips also goes, wherever it goes, they take up. And this central radio station nearby. And we have physical voice, we have pilot radio sound going up, we have radar, and we have aircraft, piloted aircraft. We have now we are using drones. We use extensively drones for so we have plenty of. We have typical observatories maintained technological. And we have a video system. All these observations all are controlled by a system called Wearable Technology Cloud. It is similar like Wearable organization. The headquarters unique. And I'm an expert member in for WMO. So only collaboration among all countries happens only under the WMO. We have good understanding with Pakistan. Pakistan data comes to us. Our data goes to Pakistan. There is no conflict because we all know that the weather cannot differentiate the boundaries. Okay, so there's a beautiful understanding. Only I think WMO should get the lower place of peace because there's the organization bringing all. When we go for the meeting, all countries come together. Because they all need our data. And all these surface observations were typical technology observations. They take observation, extract, code the observation. Then we follow it and got universal coordinate. Nothing but game VTC. Zero VTC is morning 5:30. Morning 5:30. So morning 5:30, whole world is taking observations. Surface observation. And we exchange through our television. Then next observation we get 3, 8, so every 3 hours.
Then some kind of data assimilation.
Yeah, so then all the data comes up in Noida get all this data from IFD, and they archive this and first of all, they do a quality control, and all the data is good. Then we have a protocol for quality control, and once you do the quality control, once the qualified data goes into assembly.
It's kind of a interpolation exercise.
Data assimilation, nothing but finally, if you want the equations, if you really want to always using binary difference, you need the printed form. It's great. The observations are periodic and it's not in a regular grade. So we need to interpolate into a regular grade, more regular grade, and the data consistently physics wise it should consist.
It's kind of a mathematical.
Yeah, we use a method called ensemble column. Ensemble column. It's a method we use it for our data.
So I guess the question is, maybe there are a variety of different ways to do this.
Because data assimilation is entirely a different ballgame. I say that people can talk about others.
Do we have enough expertise?
We have. Not a, but we have. They are well trained. We are well trained. But there is a lot of scope for improvement. We are working on that. We are working on that. And also a new method. See now when you are a coupled model, the associate model will be assimilated separately for most big data. Ocean will be assimilated separately to ocean data. That was the area it was going on, even now. But that gives a lot of difference. The ocean energy is fed into the atmosphere. And atmosphere energy is fed into the atmosphere means drives the ocean circulation. And for example, latent will ostensibly driven by atmosphere. So this both should be consistent each other. So when you do the assimilation differently, there is a mismatch. So now a new concept got coupled data. So you data assimilate, put it together and do it together so that all this ocean and atmosphere comes together consistently. It should be.
Yeah, because ensemble, Dharma's building is just in a B-square optimization.
Certainly, that's it.
But there are a variety of other ways to be optimized.
There could be. You can I think you should people in enzyme believe there are two groups out. But they don't do basic. Basic is a basic probably. They don't do. No, they don't. They apply our own methods and
Those methods are being developed in
Europe. Basically, the European Center for Management of that's UK. That's a center where they all do research. Basic. They do extensive. It's a joke. When you go, if you go with enzyme with the pen drive, they will make sure that all the data in the pen drive are taken by the Mac. So they say that you don't take any pen drive. Then what little means they use all the data. They don't go any data. They do even own data. They will ensure that it goes. Because the ultimate aim is to make the user. And if you want few data, even a small set of data, it doesn't fit into, they change our data assimilation package so that this data also is available.
Are they using less data for India and everything?
No. They are the people who use maximum number of surveys.
Maybe India selecting less data.
No. There's no selection. So this, I asked the same question. For example, the initial condition prepared by ECMW, and the initial condition prepared by ECMW. There are different. Same day. I asked the question, why how can they use some data which are not available? They use more data which are not available. I asked what are the data? So they have some countries, especially salary China. They have salary data. They are not available. They are available to us. So if we use 80% of data, if they use 100% of data for India, we use 85. We use less number of surveys than is in them. So obviously there is difference.
For example, we have less data for
but the same data goes to someone.
because they're getting less, because they're getting more, they have better fit for Europe. They have
That kind of thing. Once you put the data, the data is understand from where it is, from the whether it came from Europe or India. They don't pick up. You mean to say that data rejection? So that if there are less number of observations from one region, what if you want that region will be poor?
So I'm basically to the fact that precipitation goes down, can get more to make, but they are not very good. But the thing is, the fact that they don't get very well.
Okay, so I will move on. And, so these are the kind of observations we made. We say you are talking about the aircraft. The aircraft. You can see that over transatlantic is a beautiful observations for you. But here we don't get much of it. So Indian we get some. The radio zone is a purpose observation. As I said that overall land is there, we take observation and there are satellite. Plenty of satellite. If you assume that the 100 data goes into the data observation, 90 data comes from that. So satellite is the main input for it. And another interesting point is if 100 data from satellite, only 80% of data goes into really data. Remaining all data goes into the even satellite data because they do quality. So when the quality kind of even satellite data, huge number of volume of data, it doesn't really go on the data. So the emphasis is on improving the data, satellite data quality. So there the algorithms of the temperature. So there's a lot of research going on in satellite, is not satellite before. Where the satellite sensors are how the satellite information can be used to derive better products. Okay, so these are different satellites we use for Earth system observation. You can see that's a huge number of satellites. And this is the basic equations of the morning also. Now talking about this is the momentum equation in U, V. Wind can be divided into horizontal component two ways, U and V. This is the vertical form. U, V, W. And this is for U, this is for V, and this is for W. And this is the continuity equation. And so this is nothing but FPC with MN. Nothing but FPC with MN. Okay. And so that's why I put the Newton's proposal here. So du by dk. So in this is the correlated force, this is the perfect gradient. So in the x direction, the perfect gradient force is the main driving force. In the vertical velocity, there is no perfect gradient. It's only the pressure difference in the height. And so if you really do the scale analysis of this equation, the vertical with the third equation, the dw by dt will be zero. Because the value of vertical velocity in the typical atmosphere is very small. Horizontal wind speed could be 10 meters per second. The cyclone will be 30 40 meters per second. Whereas vertical velocity will be 10 centimeter or 2 centimeters per second. So in general atmosphere, vertical velocity is small. So this parameter, this can be put as a zero. So then basically this is a balance between this term. So that's why we call the atmosphere and general atmosphere. But this hypersonic balance will not be there for a thunderstorm. If thunderstorm happens, there is a long vertical velocity. You can even up to 50 meters per second. So then this equation, this part is become very important. So then generally the models are hydrostatic. So this equation will be only last part of the system. But for the thunderstorm prediction, the models are non-hydrostatic. For example, WRF models they use, the models are non-hydrostatic. So if you really want to predict thunderstorm, don't use the hydrostatic model because the basic concept is wrong. And this is the continuity equation. This is the conservation of energy. This is the dynamics. This is the base law. For the oceanography, the equations are almost similar. So instead of here, the main difference is ocean is non-compressible. So there's an incompressible equation. The equations for incompressible. That's all difference. And also there is a pressure conservation, nothing but conservation, nothing but is a balance. The main equation separately for a science. Okay. And so basically, equation, how you do it, you start with the initial condition. and you use the forcing and multiply by delta type, you get it.
Much larger than the you were talking about. That can be
You mean to say that atmosphere can be considered?
because the thing is, the velocity ratio, how the velocity is much smaller than one.
Again, in geology, sound waves are not at all. They were protected. Sound and wave use. Generally, you can get them control.
After why is that you mentioned that earlier?
Because speed are different. Speeds are different.
So you put them in, then you get wrong.
So Richardson did the same thing. He did not repeat the work. So we do the way equation when solving it, first you figure out the sound wave, complete number of it, figure out the reactive wave, then you can get a further response. So meteorology waves will be retained, depending on this. We don't, because they are not worried about sound waves.
So this equation, how many, this is a global level, right?
This is like every grid point, you can do this. You know the equal container.
How many calculations are going on at each grid point?
It's a 4-dimensional. So I'll tell you how much it will be.
So per day, this is begin to calculate.
Yes, sir.
And then grid point itself.
Depending upon how much is the response of the model. We use 12 kilometers. Now we are going moving to 5 kilometers model. And basically, we use 64 kilometers, 64 levels per kilometer.
So that will be the grid point.
Well,
Per grid point.
it's so interface. Depending upon how much you want to cover. If you want to predict only 2 days, fine. You calculate. And there is a relationship between delta T and delta X. In the numerical method, there is a relation between delta X and delta T. You cannot use any delta T for any delta. There's a relation called CFL Precipitation or numerical. C is the velocity of the wave. C delta X by delta T is less than. So the meaning is if your delta X is small, that means your resolution is small. The resolution is high, because of 1 kilometer. Delta T can be small. Few seconds, few millimeters. So I think you can get more of more dust. So that's the meaning. So this is all related. And so we use two methods. One is time derivative is basically finite difference. Spatial derivative is there are many aspects of this finite difference. And the spectrum methods. So spectrum methods are not used. Very different. And interpretive finite difference spectrum methods are now used for. So this is the way programs the whole group can be divided in grids, and each grid calculation will be done. And also there's a adduction, so there's each different grids are also connected. Okay, well, it's not very independent. Okay, there's a lot of adduction there. And this is the ECMW of particular level. You can see how many levels levels. And the distance between two levels over the copper atmosphere is much closer. But if you come very close, it will be very narrow. Every 10 meters, every 20 meters. And this is a new grid has come. It's octohedral grid. It's a new concept. It's recent again. And we are in India, IIT Pune. This I don't know much about it, but then this that can somehow it can really give much more better results. You can see the each grid is not square. You can see the kind of a triangle kind of. And we had in the ADM grid that we really use the Cartesian grid, and we have a problem about the poles. It's not the same. The area here and the area here is we had issues. So this is all that we can have. And IATM has so this is the data assimilation which I include. And the model also has a physics. The thermodynamic equation green is all this is term for diverging heating. Nothing but radiation, false, Atlantic boundary layer process, and these are the different kinds of physics which you use for parameterizing in the model. For example, how the solar radiation is coming and how is getting the reflected with how the aerosols And there's also long wave radiation going up through different gases, and this is convection, shallow convection, deep convection, big clouds, and precipitation, big waves. Then over the orography, there will be a track or orography track. When wind flows over the mountain region, we get so-called orographic track, and we have turbulent diffusion, then other chemistry, we have ocean, we have surface. So we all need to use it as so then a cloud access, and if you use a 50-kilometer model, the cloud is only a 5 kilometers. Okay, so the cloud is within the 50-kilometer model. So how we treat the cloud, you have to use indirect way of treating the cloud. You can explicitly use. So that's the we call parameters. We have to use cloud as a parameter. We have to use within the grade 50 kilometer grade, how the cloud forms, how the condensation process, and how cloud will look. And once the condensation process, it basically it releases the energy. Basically, it heats up the atmosphere. Basically, energy, and that energy is driving the atmosphere. Okay, so we need to really treat. And the basic problem in our future, I will be talking about this cloud parameter. We are very poor. Models do very poorly in the cloud parameter. We don't know much about it. Maybe one of the reasons is cloud doesn't the sky. If it is somewhere down, we will have brought it the cloud into the lab. So we have observations, the aircraft going in the cloud and the observations. So we cannot do an experiment with the pixel. And this is how the brain process. Even now, I will think about this. You will understand how you can make a prediction for rain. So rain process is the rain process. And how much is involved in it's how many processes are involved to get the prediction of rain. There is a cloud water, then the process called auto conversion, and how the accretion is happening. Some hail will forming, and hail can really give rise to rain. So much complex process, but we know this process not in very detail. We know very well. It's all basically it's about we understand it, but there could be a lot of errors. So if you make any small mistakes in making parts of autoconversion, that will lead to the forecast. Understood? So this is the area where AML we use it to understand how the autoconversion. You don't worry about what autoconversion. So this is the area where it can. AML methods will succeed where the physics doesn't. We don't know much about it. So that will be the place where AML methods. And this is the butterfly effect which Lawrence Krishnan also was talking. So he is from MIT. He tried to solve an equation. And so he started with initial condition only 6.8 and 6.853. Okay, and you see how the final output is after a few times, a few hours, completely level. So then that is the process. That's the time he told that our forecast, especially weather forecast, because certain different situations is very sensitive to the. So if we assume whatever observations you use it, there could be error. So this is the equation he used it, and the way he started. So this is the you start from initial one initial condition, but after a few hours, one can go to this regime, another can go to this different regime. And this looks like a butterfly, isn't it? So we call butterfly. So any small perturbation in New York can cause a big heavy rain in New York. It's a butterfly effect, we say. Okay, so the concept is that forecasts are very sensitive to the country. So you have to be prepared with it. So there is a chaotic element comes in there. And that's why we use ensemble. So you start with one initial condition and produce one forecast. This is a deterministic forecast. Just a forecast for one value, you can get one value. But then you can also initial conditions, you can perturb it. You can have a scenario for a forecast. Then you can get a broader spectrum of a forecast, and that can be used to calculate the power. So that is the method we now use to follow. So deterministic forecast is good for next 2 to 3 days. We are 3 days to say all forecasting. That's what our concept now. So So for any forecast beyond 3 days or 5 days, we use stochastic.
Previous picture, you say probability of impact. So, saying how many models predicted.
How many, for example, this is the probability of precipitation presently? How many, for example, you have 30 examples. 30 examples, what is the probability of all these different categories? One model will be predicting 2 centimeters. Another model will be predicting 5 centimeters. Understood? So for each of these report, you can calculate what the probability of 2 centimeters or 5 centimeters. So if the probability is high, that means you have more confidence than that. So I will give an example. This I don't know. This is not so good. This is the way we use seasonal forecast using example method. We run some 30 examples and we calculate below normal category, normal category, above normal category. And this is for the forecast for this year. You can see that every year most of the places is not above normal. The model is predicting high probability for above normal. Above normal means the whole monsoon rainfall is divided into 3. That's the week of the side. And so first 33% is above normal, middle is normal, bottom 30% is below normal. So each from model forecast you can calculate what is the probability for above normal, normal, and below. So this is the information which we give to the person. Okay. So we have so people here can understand that model is predicting, average is predicting above normal rainfall. And also the predictability important forecast. As I told that the atmosphere starts with initial condition, but rapidly it falls. So initially the short-range forecast is good for 1 day, but it drops sharply after 3 days to 5. Over the middle latitude, for Europe and US, this graph may originally this big. Whereas in India, this may drop. That's the difference between, that's the people are, oh, in the US forecast not good, but in the US people are predicting better. Because the weather systems in the US is different from the weather systems. Okay, so they are not very sensitive to it. But our weather systems are with more sensitive to it. Okay, so then there's a small predictability comes in extended landscape, small predictability comes in seasonal time. So we have started a monsoon mission in 2012 to improve our monsoon forecast. And this is again the forecast, sorry, the diagram which slide which Krishna was showing that how the forecast improved last 20 years. It's been a substantial improvement. As I said, the southern hemisphere has improved because observations have started coming after 2000. And now the 5-day forecast area is now equal to 7-day forecast or 3-day forecast. So we have improved substantially, but so for last 30, 40 years, doing the intensive research in observation, putting more observation, doing models, we could improve forecast by. You understand how bad our situation, how difficult our situation. So we could improve last 30 years, but in days of.
These are now exact forecast.
These are deterministic forecasts. Basically, if I had to read one paper. Let us remind about 5.6 kilometer, what is the height of that object? And you can also in this case, 3D forecast is outside of plan. It doesn't really improve. So whatever skill we have, it is not improving. But what is improving is the forecast in the longer time. That is mainly because observations are improved. So if the new data and conditions are improved, so it is going beyond that forwarding the predictability. Physics also improved. We know the cloud process, etc., very far better than. This is the last, I think this is the last one I'm doing this presentation. These are 4 maps. One is observation, remaining our model. Can you differentiate between these observation? One is observations and remaining all of models. All looks very similar, isn't it? That is the beauty of our present environment. This is observations. This is satellite observation. Now, this is that model at 1.4 kilometers. 1.4. This is the model at 9 kilometers. This is the model 9 kilometers, but it's different, without difference. So we have, last many years, we have improved a lot. Still, we have a lot of many years. We start now or take a break? Take a break. Make a 5 minutes break. Only one last part. We should stop for what time?
Will we try to stop it?
6 o'clock. Then I will continue.
No, but we can go another, we can take a break.
Okay?
So what time is everybody knows that dinner is at 7 o'clock. It starts with 7 to 8:50. And then that dog here or people. Yeah, online, you can do it online.
Okay, so.
Outside cloudy.
Ah.
You don't know much about. There are a lot of gray area. I bet the third specific kind of parliament. The precipitation comes from clouds. The clouds are not good, precipitation are not. See, models are too good for wind stability. When it comes to precipitation, is the problem.
Marking is for elsewhere, not so much marking.
Much of it. Not is very rarely good. My student has done PhD. Only, so if we assume that the 100 papers in Southwest Conference, so it may be a right. But there's a lot of scope. And they are saying
It's a description of the code, if I wanted to write the code from the scratch. With all the documentation. I can model the data.
it's available. We write in Photon. We use Photon. Documentation is up. Even code. All the codes are panelist. For panel course.
But the models you should run on top level.
So WRF model I say, you can already run in the laptop.
Without laptops are also much faster.
Much faster. And you get into the bus computer time, much more better than. And China, I was told even school students, they run the WRF model. To see their forecast. Just for a fun. You will learn a lot. This is a community model. So many people engage in model. For example, if you develop a algorithm, the group will test it and put it in the lab. And they will acknowledge. Community model is now better. You cannot, one group cannot really. ECMW does it themselves. It's a commercial. They give it to only European countries. Remaining focus on, if you really want, you will pay. If the funding comes from all European countries, so they work mainly for it. So therefore, the results I give everything is built up.
Because the Indian one is
Pardon?
Indian medium range forecasting.
Indian madam, please. Yes, sir, it's all available. 10-day forecast every day. So that's why cycle morning, Christmas cycle. We run 4 cycles. Start from 0 ETC and run for 10 hours. Then at 6 ETC, then 11:30, run for next 4 days. New data, 4 days. Then again, 20 ETC run for 10 days. Then 18 ETC run it again. But huge computing power. Because thunderstorm, the 0 ETC you run it, you cannot get it. But if you run it with 60 ETC data, thunderstorm comes in the evening. 60 ETC means more closer to the thunderstorm event. So the probability of getting correct. Model doesn't give a thunderstorm.
There was one.
So there are some indices we can calculate and there are some thermodynamic indices. So the model, so it gives the rain, but rain need not be thunderstorm. Even without thunderstorm, rain. So thunderstorm, there are some standard indices, thermodynamic indices.
Even rain, how do you get?
Pardon?
Even rain, how do you get? Could you look at the
The rain is a problem. Rain is a problem. Let's say rain is any problem. Rain is a variable, output variable.
But that does not mean it's ability in the model.
Humidity, then is the cloud model, the humidity, everything is transferred into cloud condensation, cloud liquid water contact. And now liquid water contact, you can do pardon?
The region is the very.
The precipitation is, so that also you can differentiate between the convective rain and stratiform rain. That also is. Yeah. Excuse me.
Sir,
That would be. Yeah. Thank you. Can I talk? Yeah, so this is the last part. So I think we should stop him whenever it's required. So I have a tendency of speaking more. 40 minutes? 40 minutes. 40 minutes. Yeah, 40 minutes. Right? Next one. Yeah, these are the models which MOES has, Nowcasting has. They have a model at 400 meters. Used for the airport. So it's very high resolution. We have a 330-meter fog predicting fog over the airport. We have 1.5 kilometer for this model is being used. Then there's the 12 kilometer global model. We have a global ensemble. Then we have a coupled model for 32 kilometers for the percentage and system class. And here the ocean is coming. Here there are not ocean. Here no fish model. Here ocean is there. We have 150 kilometer system model which is using our plan. And this is the ensemble prediction system 12 kilometers. To be one of the best models. And we have two different systems. Same person, but two different models. Delhi air pollution model is the air pollution model, prediction model for Delhi. Predicts the air pollution levels. It goes up to 3 days in the flight. And the resolution is 400. Grid point. Every 400 meter you can get a 400 meter.
but here the position being related to stochastic, right? Some people die, like their car or.
Yeah, so the source and the source are known. So we discuss the source.
You know, allow them to be stochastic. How good is this model?
Good. Yeah. There are a lot of gray area, but when the big events happen, when the laying of from just maybe a few numbers in this section, but my model just picks up. Picking up and up model.
But just Delhi based enough. So that's you saying that Delhi is only affected by
It's only Delhi emission scenario. So in this case, we usually got it. If you want to do it for Kanpur, then you need a Kanpur water resource. How much they different.
But in a sense, Delhi is not being affected so much by environment around.
Yes, sir. They use it so we use the forum to be a solution, but the model is a big model. So objection, for example, what is happening in Gurgaon when you come to Delhi?
How far do you go?
Looking at the area. I have to remember. Yeah, Punjab. biomass money, the performance problem. So it is itself in the model, so available in the model. So that how much biomass money is happening, it can be measured using sampling. So that is not Modi. Modi can measure how much fire is coming. So that fire count can be translated into air pollution sources. Air pollution source. So that's the input for the model. So it's covered, but it's both of the almost Punjab. Sorry, Pakistan. Almost Pakistan. But more concentrated over. And so this emission scenario, we want to update it. Because 2 years back, the emission scenario may not be saying up. We updated it. Okay. And so this is the ensemble forecast system. So from the Indian perspective, how our forecasts are good. So it's started from 1999. And this is the RMC, root mean square error. The less the error, then the forecast is good. You can see that beautiful decrease in the forecast. Some years, you can the initial years, the decrease is not very appreciable. But once the model resolution has changed into high resolution, it's causing substantial drop in the RMC and also this. And this has also happened, as I said, that the forecast in the 3-day forecast, 5-day forecast, so 3-day forecast a few years back, now it is a 5-day forecast. So India also, after many years of work, we also could achieve 2 days of improvement. Because we have T1534 models. So as I said, then for rainstorm, this is a serious problem in all the models. The model, this is the for 1 day, 2 days, 3 days forecast, and these bars are basically the observation, and the lines are actually basically the model forecast for different models. And you can see that the model over predicts these are different threshold of centimeters per day, and you can see that the model over predicts the lower rain. The light rain is over predicts. It goes on telling that it will be a rain. But when it comes the heavy rainfall, maybe in the right hand side, the model has predicts. So this is a universal problem. It's not only for it, it's a universal problem. The model over predicts the light rain, but under predicts. But what we really need for a kind of a warning system, or early warning system, right hand side should be better. To tell about heavy rain. And also the basic problem in our model, it's a new area where my student cannot we need to work on when the weather system forms, it takes a lot of rain. But in the model, the weather system is really up 24 hours. The model will be predicting how the weather system is moving. But in the model, what will happen? The weather system will be there in the model with the same minutes. But it is spatially discrete. Understood? So it's a spatially discrete. The center may not be over Nagpur, it may be slightly away. But that gives a lot of difference. Where the system is giving rain, system is there, the model where only will rain, but actual rain is happening somewhere else. So when we verify, when we do a box average, we are doing 2 times we are analyzing them. Where the forecast is, where the weather system is there the model won't predict, so the difference will be very high forecast difference. But where the model is predicting system, where the actual things are not there, so there we are giving twice the analysis. So then there's a new method called contiguous area. What we do is, or we only use for verification. We take this system, the model, to actual using a correlation. How best we can correlate with the actual occurrence, the contours there. Then so then you can calculate how much error in the spatial dimension, how much is the volume error. So we have better understanding of what really happening. It's a new method to get emerging areas now. And this is also different kinds of forecast. You can see that the day 1 forecast for bias is the probability of rejection. You can see that this is for 2 centimeters, 5 centimeters. And for day 3, you can see that it's substantial improvement over the years from 12 to 10 years or so. There's an improvement in the probability of rejection. Even in 5 centimeters, small increase. So there is an improvement happening where, so wherever Funding is required preference of a, to show this map, saying that we are doing stuff, so it gives us more money. It will improve.
So in what way are you improving? What are you doing differently?
As I said that the models, the resolution has increased a lot. And also the data is both in the, we use a better data method now. More data is going to, number one. And the ensemble column variation is too very different. Getting from the 4D variation. Okay. And this is for the active brake cycle of the, this is the actual observations of a brake cycle. You can see that the range is there only over here. Of India is not very. But the model also was predicting this. So this is the day one, day two, day three. This is for Kerala floods and the last one country in trouble into August 2019, very lot. And this is the actual observation. You can see how much rainfall has happened. This is the data which I mentioned about. We are putting salary data and range data. So this is the data sets. It's available as it's available free of cost. This is actual observation. And this is three different models. This model is not making up very well. It's our Indian model. So this is easier from Indian model. This is also Indian model because this model is predicting better. And this is the very controversial paper just comes my colleague in ATM. This is actual observations for different days. And what this is actual observations. These are different class. The lines are the small lines are different class. For one dimension, one standard deviation, two standard deviation, three standard deviation. And you can see that this model is predicting two standard deviation good, and this also is predicting two standard deviation good. But this IFT's DFS model was not there. So the rainfall was so big amount that some models are not able to predict the kind of extremeness of that rainfall. So you cannot predict if the rainfall is more than model won't predict. And Kerala flood in 2018 was more than 2%. And this is the thing which I was saying in the morning. The flood warning system for bombing. We have got different warning. The basic inputs is rainfall. How many rain is covered? Then you have a hydrology model which takes water everywhere, flow. And we also where the ponds are there, where the lakes are there, where the river is there, small rivers are there. Everything is taken. But the basic data is the rainfall. So we run a 4 kilometer model to prepare the forecast for rain. This is a forecast 25. This is actual rain. Just data. 25. Actually, theoretically, it should lie in this 45-degree line. If you put all the data together, this is the way. Sometimes it over predicts, sometimes it under predicts. And so if you flood warning system, you might develop a very sophisticated model. But the basic input into the model is the rainfall. And if the rainfall is not good, this system.
I think always we will push
Yeah.
so that the rainfall model.
That's the case done it for Chennai. No, it's done it. This is actually economical.
What are you doing? That's your model.
This is a model. This is a model 4 kilometer model, and this is the actual observation. This is forecast for different days. This is 14 July, 15 July, 16 July, and something. This is actually so. For example, this on this day, there is a lot of rain from up to 200 millimeters at that particular point, particular rain gauge. But the model was not predicting anything. Model was predicting anything less than 50.
Model is only taking Mumbai as input and
how we run the numerical model for higher resolution 4 kilometer model. We run a 12 kilometer model. We take the boundary condition of 4 kilometer model, and then we run a 4 kilometer. So it's a kind of embedded model. Model is embedded. You need a boundary condition. You cannot simply run a. You need a lesser condition.
so there is 12 kilometer for this the world model.
It's a global one.
World is the
Global one.
You can't just take a quarter of the world and then you can't take substantial portion of the world. You have to take about
whole world. So we can prepare quota for other countries now. We give to all of them.
But the philosophy is we learn our coastal models before going. And get initially can be from there from finance.
And this model is run only for next 2 days. Doesn't go. As I said that if you go for a higher resolution, you cannot go for a long time. If you use the quota resolution model, you can go. That's the philosophy. Yeah, and this is the, as I said again, the quantitative distribution. For plain body, how much the water will go and how much water will go up with level basis. So cellular water temperature needs quota of empty, say that next 24 hours, how much water can go, water will come from sky at different regions of the sub-basins of the. So that's the quantitative distribution. This is the toughest problem we have. We are able to predict rainfall, but the amount of rainfall, what CDPC was, the Water Commission needs is actual amount of rainfall. If we don't have, they don't have actual amount, then how they count it river flow? In terms of cubic meter of per mega. They don't calculate. They need actual forecast, actual amount. What is the distribution? Not only for India, any part of the model is performed. Okay, so this is for example, I given every day, this for different models and this for different threshold. This is for 100 millimeters. You can say the heat rate. Heat rate is how much we can. Is the ratio of the prediction coming. You can see the for this thing. This one, this is 0.2. I mean, if you use the 100 quota, only 20%
On that question, what one would be to do a sensitive plan kind of chip parameter is most sensitive to producing rainfall. Then ask for the physical model that one takes that. There is no understanding. So the parameter that we use to rainfall. Why this gap is.
We have studied. Another analysis here now. This is basically the cloud micro. This is the problem with the cloud micro. Cloud micro, but basically the cloud. See how the cloud forms. There's a lot of voice convergence. Air comes down, up, then goes up. All this convergence and all is model plays very well. Pretty well. You have to 3 days, 4 days turbine. What the cloud forms? The formation of cloud within the cloud, that white is how the water vapor condensated. Then the cloud the rain process. There are different kinds of different. Warm cloud, the process, process is different. Or ice cloud, for example, the height of the cloud goes beyond 0 degrees. That can be slow. That can be hail. But if the cloud is below 0 degrees, then there will be only warm cloud. Only rain can come. Precipitation can. So the physical process is physically the two droplets form joints to the coiled. Then it becomes bigger. Without getting it takes a more very important aspect of the the X amount of water is going up, gets condensed. The same X amount it doesn't come as it comes in a smaller. And how much coming it can vary from day to day, it can vary from different stuff. And we care the cloud efficiency. Cloud efficiency. Normally the cloud efficiency is very small. You must have heard about cloud burst. What is it? Cloud burst. Cloud burst, what happens? This efficiency is very high. Because very high. If you X amount of it is 10%, 30%, 40% of water vapor condense, the cloud will form a survey. So the question is, why in some clouds it will be 50, right? Why in some clouds it will be
radar signal that
it can happen. By the time you receive an radar, it must be raining there. We need to tell them in advance. Okay? When it is raining, you say it's raining everywhere.
because we are not looking at cloud when it's not it's the prediction cloud. There's a cloud there or not. Whether it is rain or not, it will be like
Okay. Clouds have very small lifetime. For example, you get a cloud in the sky, you put your name, something, allow the cloud to go. After a few minutes, the something's name will go. The process, the physical process of cloud formation will remain there. So the particular cloud will dissipate, but another cloud formation will happen. So the process will still continue. The same, if we track good cloud, it will not be seen there after few years.
So it's not that lots of them and other. I will say any exact information to data.
So the data for understanding what is happening, but it cannot give a predictive value. I guess that it can give a value for 2 hours. For the next 2 hours, when how the clouds are forming, how the clouds are, where the clouds are moving. So now the thing it can be used, but not on 1 day, 2 days.
So this is the open area.
Can we consider this of
Alright.
how can happen the same control? Even if you are. Can you predict if the cloud will?
Yes, if it is tracked by radar. If it is tracked by radar. That's the basic concept we have now, Nowcasting. That's why we are putting a lot of radars in the western, northwestern parts of the India, like Narayan. We are putting because cloud-based is very common there. So you cannot predict in 1 day before that cloud is. We can predict rainfall is going to come. Whether it is cloud-based, cloud-based is different 10 centimeter in 1 hour. 10 centimeter in 1 hour. That's a cloud. That's a cloud. So that amount of rainfall will happen or not, very difficult to say 1 day. We avoid before we get 1 hour before we can calculate the rainfall, what is can be expected from that cloud. So you can say, and if you know that how the cloud is moving for next 1 hour, we can. But not more.
Like, that are coming from up, can get it down.
Radar is the ground, it rotates, scans. It has an angle. I don't know. Okay, so this I move. This is the local cyclone prediction, you know, it's the lot. Now the next new concept is coming is extreme weather. Like we cannot predict whether it's beyond 10 days or 8 days or 7 days. The predictability is poor. But extreme weather also, we can predict a normal rain. Extreme minutes, 50 centimeters, 20 centimeters. We have models on. The new concept they call extreme weather. Why it is the model has a bias? The model has overestimating lower rainfall, underestimating the higher amount. So the model has a bias. So if we really calculate the actual amount of rainfall data for the model and it will be wrong. But the model has its own climatology. Okay. So instead of actual observation, use model climatology, calculate the extent. Don't use actual observation. If you use actual observation, the extreme won't come. But model has its own climatology, model has its own extreme. So the extreme, that extreme model extreme is not the same as the model climate for the observed extreme. But model has its own climatology and climate. So you calculate, you don't forget about the what is observation, but forget only about model statistics and calculate the extreme. You may have a bias. So basically what you do is you remove the bias. By doing that, you're removing the bias. That is a beautiful method which people have started now. Your IIT Pune has started. So this way you can calculate the extreme for rainfall, wind speed, everything you can calculate. So beautiful example like that. This is the rainfall happened recently. Andhra Pradesh, Telangana, a lot of flooding, people died, a lot of casualty, a lot of damages. This model is IIT Pune. It's basically just called extreme forecast. So you can have rainfall. Basically, it's a model extreme value. The model, but this may not be same as much fluctuation, but it will give an indication that this extreme event is going to happen. So this is extreme intelligence is not possible. Very large number, close to 1, very high number. This is the one day 1, this is the day 2, and this is the eastern of we can see that beautiful. So this will give an indication to a forecaster that something extreme is going to happen. You are not able to tell not exactly the amount of the model climatology is different from actual event. But it can give you an indication that the extreme event is. This is enough good enough to tell the collector saying tomorrow is going to be heavy rain. Make sure. It's safe.
This gives the indication that could be a
Yes, it's a beautiful concept. They're improving a lot. Okay, this is the only way now we are able to solve. To some extent, of course, this also can go wrong. I'm not saying that everything will work. It also can go wrong. I'm sure it can go wrong, but it is improving our. It is improving substantially. New concept, basically removing the model bias from the. Alright? It was there in the forecast, but I don't know how many people have seen that forecast. So putting in the website is not enough for the user should really see it. Also, user should be able to make use of. By saying it, so what? Something Kerala last day, IMD has given a forecast for rain. Maybe what will happen over last day? Oh, that reduce by why not 80. But question is whether that the heavy rainfall will lead to a landslide, nobody knows. So even if you tell the Kerala government is going to rain, it is rain. Okay, so unless you say that it is going to lead to a landslide, you will take action. 2013 Uttarakhand forecast, same thing happened. IMD issued a heavy rainfall forecast, but they did not say that it is going to lead to this kind of thing. So for people, district like they have hundreds of problems. There will be violence, there will be other issues like plastic issues. So to tell you that you take action unless you give enough information, you know, do it. So there is a big gap. Okay, so I will move on to. So this the so-called isohexagonal model, Auroop model is doing a lot because we have recently done some exercise. So now IITM, IMD and IITM is going to a 5 km global model. It's the Auroop. It is giving a much improved forecast. The extended forecast, we have a good forecasting system, and this is the skill. So as I said, that if you go for a longer time scale, you cannot give just very high resolution. You can only subdivide the give. This is the skill for peak one, PG up to 4 weeks, peak one, peak 2, and peak 3. After 2 weeks, the forecast is pretty good. So skill is good, and the point is classic point 4 also. But in the week 4, there is no skill. We also do some. It's called extended forecast. This is a seasonal forecast where I have spent a lot of time on monsoon prediction. I spent over 20 years monsoon prediction. So we started from 1886. The first forecast was in 1886. So India was the first country to prepare a seasonal forecast in the country. 2016, we produced the forecast model and usually we have, so 2007, we introduced a statistical model. What we use this as a predictive, and then some of the predictors we use, and then we run a statistical model. What we do is we use 5 to 6 predictors, and there are 2 ways of doing it. For example, if you have 5 predictors, you can write a multiple equation with the 5 predictors on the right side. Okay. Or you can have predictor with the 1 model, 1 predictor. You can have a model with the 2 predictors. You can have a model with 3 predictors. So if you have n number of predictors, you can have 2 raised to n minus 1. Okay. So what we did is each predictor, we did not fix all the predictors. We use all possible combination of the model, all possible combinations. Then use the criteria to select the best fit models. Okay, so then that model we used in example average. And one is a linear model, simple multiplication linear model. Another is a new method for nonlinear called pursued projection regression. Pursued projection regression. This is a nonlinear model. And so these 2 models were used, and we extend as become back to this we use it for all these data are not available for. We have a data about 51 now. Okay, so this model has some. This model is still being used by IMD for seasonal forecast. And then you can see the skill. You can see that after you introduce the skill has improved substantially. And then we use dynamic forecast that we followed extensively everywhere. And this is a model which usually we have the model called ensembles, which is produced by European group. And this is a consumer model which we use, and this is the skill score. For all India is scored for derivatives initial 3 and 3.3, 0.46. So if you go for a longer time scale, the skill may not be that good. The correlations are only after 0.5, 0.6. You may ask a beautiful question. I told about predictability and robotic system. So you cannot really predict beyond 7 days or 8 days. Question is how we then predict the system? We make a system. This is about the next one season. And you are doing that is another robotic. You cannot predict more than 5 days, 6 days. Answer is on a seasonal time scale, this boundary condition like water, soil condition, snow cover. That varies on a longer time. Okay. The influence of possibility, influence of lavina, you can have an influence of season phase. But that happens on a longer time. So the boundary condition plays important. That's the basic premise of seasonal phase. Otherwise, you will not have been able to predict.
The chicken forecast is a big number for I do we are saying on March 21st, May 21st, what will happen.
We have a small number, one number, or one season.
It's a different ballgame.
It's a different ballgame. You know what? But it's very useful. Very useful. If I am giving a forecast one day later, what is the Prime Minister office will come? $1 million saying that what happened with the forecast. Those people will be wondering here and there and will ask what happened with the forecast. So they are all watching and waiting for our very important forecast. Only is a kind of an impression saying that this is going to be good. It will give a good feeling.
But you mentioned that slide very quickly when you show the actual and the forecast.
Yeah. So these are statistical models.
Pretty good, right?
Pretty good, pretty good.
Still have only 8 parameters, but they have been.
No, we have only 5 or 6 parameters. Maybe there needs to be a 16 parameter model. 16 parameters. The variable one to equal was there. We was that again.
Some years where the forecast is off like 1994.
Yeah. Yeah, 90, and here is very good story. 1994 the forecast went out. 1994 I was in research and doing my research and I was very comfortable. So when the forecast went bad, the DG called, IMD called and they were said, I don't know, I have people to do it, etc. Then we transferred it to forecast. That's the reason I joined Matsuri. Otherwise, I was working on aerosol and cloud physics and I was happy. That's from 1994 I started chasing money. I tell you, it gives you a lot of trouble. People will abuse you, people will control forecast, go on the wall.
Election forecast.
I have 15 years of forecast. I am not sure, I don't know whether I should tell all the stories. From 94 to 2008 I worked. 2007 I introduced this model. 2007 forecast, first forecast was not so good. So many people criticize. Of India, wrote an editorial on central page saying that I am to introduce this model. Very visibly, the person who was about me. So this is not the basics of mythology. The basics of mythology. It is the central page. They want to criticize government. They choose me as a scapegoat. 2008, forecast was on bullseye. It was perfect program. You can see that 2008 forecast.
But not 2009.
No, I tell you, 2008. It was perfect forecast. I thought this is the best time to be my. I just okay, so I move on. Okay, so this is how the models are performing. We have hundreds of models. These are problem system forecast. But still, see, this is I don't know whether you are able to see that it's a yellow here. This is basically the drive. So the models are predicting the drive. The drive bias in the model. The rainfall amount over circulation area is much more less than that. This is a new other model. It's a new initiative called North American multi-model ensemble. That's also giving. So the skill is not that good, but it's improving. This is scope. This was scope, and there are a lot of issues. Seasonal forecasts are much more complex than interpretation. That's not the next 5 days. This is again monsoon. This is for monsoon rainfall from observation. Actually, this is the total climatology. This is from one model and this is from the combined model. And the other is the combined. We again, this is the seasonal forecast also. We You can, two ways of combining. Change the input conditions and run it for different inputs. One way of doing it. And then you can have different models and put together all models. We do more. The idea is, because seasonal forecasts are basically stochastic processes, that you need a probability. So you need more number of observations in some way. You can calculate your confidence will. So you make use of maximum number of. So that's the basic idea. Model has the previous problem. The Elino, Mr. Carter, the Elino phenomenon is happening. That's the driving force for change. So Elino happens, nothing like for Elino happens, and La Nina happens, that is other phase of the Elino. Then we have this year is the La Nina phase, so we are getting around breaks now. So and this is the correlation between the monsoon rainfall over here and excess temperature. You can see that this Elino, when Elino is there, we will get negative correlation. That means when Elino is there, this region is positive, we get less rainfall. This is for different models. But actual observation, you see that the same screen, actual observation scores denser relationship, but the strength of the relationship is much smaller than observation. The model what this means is it gives more importance to Elino event predicting. And now the new area is over there for decadal prediction. And as I said that there is a unknown decadal prediction system has come, so it has a poor skill. So this somebody was asking about decadal. Somebody wanted the energy forecast for next 5 years. Yes. Probably you must have got the forecast. So this is new scope, but this new data is coming up. It's still decadal climate prediction data are available. You can have a forecast for next 5 years to 10 years. And the system I will change. And this is the report which I told was telling you. And this is the WP, so the air quality forecast system which is available here. Yeah. So what the strategy now is, this is the strategy which I have to follow. We have to follow. It's a ready, set, and like our 100 minutes of frame. That means you give a long-term forecast to policymakers. Okay. Then after a few days, you say that things are still better. So you just say, ask for it. So that means first you give a seasonal forecast. Heat wave, I give you a good example. Heat wave. We give it one season before saying that the heat wave is going to happen. There's a high probability that heat wave is going to be more than normal this year. Then 10 days before you say heat wave is very probable. 2 days before, 3 days before, 5 days before, say heat wave is going to happen over this region, temperature can be this. So that is the information we give to the public. With this, I will stop. Any questions? Yeah. Before that, I'll ask you now. I have 2 slides that I want you to do it. But one slide I will tell you is the neural DCM if you wanted to. Then a new method has come. Yeah, the neural DCM which has come out just here. Nature. What they do is, as I said, that this physics here and dynamics is there. Physics is done which neural network. And in the model, this is replaced by the physics parameters, nuclear parameters is replaced by neural network. And it is, and so the advantage is that, as I said, that 80% of the probability that goes into physics. So by replacing it by neural network, you solve, reduce the computation time. And the model efficiency also is improved a lot. And of course, it's not clearly visible. You can give me that they say that compared to easier forecast, any forecast has good. We also have that, but the pending. I don't know. I least something that's 10, the Google. And they even gone into a climate state. So first time I'm hearing that seeing story about model the neural network and neural model can be used for even better. So they gone for forecast for somewhere from 1980. This is a computationally very cheap. Let's stop here. So as I said that because since you are mostly going tomorrow, we are mostly going to discuss AML method. As I said, AML can be useful replacing physical-based model.
Night is done. The two of night are also.
This there was scope, and so there are around increasing number of physical-based powers. You can improve it, and also you can reduce the computation. This is not computer time. Huge much. And just if you don't mind, I will show this slide. It's not very clearly visible. So, for example, if you reduce the model as to 30 to 5 model, how much computer time is required? It's a huge exponential. And if you reduce, do only one deterministic model is, if you want to do example, so the computing time is power is huge demand. We really simply change from 30 kilometers. I'll stop here. If you have any, this is a beautiful paper in 2015 by Nature, Scale Performance Nature. You can take it. Good. Any questions?
Any questions?
Yes, sir. Pardon?
For example, when the forecasting. That's a so how exactly decided like how much you put
So there are some objective methods. You cannot put up, you put up a little, another person put up a little more. So you have a different kinds of mathematical methods to put up. So you want to ask how much changes is happening in the actual initial condition?
yeah, like how is it decided?
So as I said that depending upon the point to point, it's not uniformly distributed. It may vary from grid to grid, depending upon the initial condition, then how much you can put up. It is based on some statistical methods. The idea is to make a broad spectrum of forecast, so that you will get a broad forecast values, and from there you can calculate the probabilities. That's a mean. Now another way of doing it now is simple. You don't perturb initial condition, but change the physics. The physics that we may be using a lot of mathematical. In the mathematical formulas, we will be using a lot of constants. For example, auto conversion rate. For example, cloud auto conversion rate. That constants can be better. We don't know the constant actual value. You must have taken observation somewhere and used it in the model. But that may not be true. So that you can, instead of 0.45, you can make it 0.46 and run the model again. So you change the physics. So that's a new concept is coming. Instead of changing the initial condition, perturb the model physics. So that's a new concept. It also works well. People say computationally it is much more easy.
Okay, well, let's thank you.
Thank you. Thank you very much. Where will we go? Yeah. Yes. Where the
That was.
again, give me the pen drive. So my pen drive is that. I can lose anything. I cannot lose my pen drive. I will end the call for now. Yeah, remove it. Sure.